Imagine standing on a beach at night, somewhere far from any city, somewhere the light pollution has not yet reached, somewhere the sky still does its oldest job, which is to overwhelm. The Milky Way stretches overhead in a band of cold fire. Not the vague suggestion of it that most people alive today have seen, but the real thing, the full thing. The version of it that every human being who ever lived before the industrial age saw every clear night of their lives, and that most human beings alive today have never seen at all. It runs from one horizon to the other, in an arc that seems too bright to be real, too detailed to be accounted for by the simple explanation that it is just stars. It has structure, it has texture. It has dark lanes cutting through it, where dust clouds block the light behind them, and bright knots where star-forming regions glow with the fluorescence of ionized gas, and a central bulge toward the constellation Sagittarius that is visibly brighter and denser than the rest, the accumulated glow of billions of stars packed into the ancient heart of the galaxy. You are looking at your home, not your planet, not your solar system, but the larger structure that contains both of those things and everything else that has ever mattered to anything that has ever lived. You are looking at the Milky Way from inside it, embedded in one of its spiral arms, roughly 26,000 light-years from the center, in a position so ordinary and so peripheral that the galaxy's architects, if it had any, would have chosen it as an example of an unremarkable location. There is nothing special about where we are. We are in the suburbs of a galaxy that is itself unremarkable among the hundreds of billions of galaxies in the observable universe. And yet, from this unremarkable position, we can see the whole sweep of our home structure, and it is magnificent, and it is moving. Not drifting, not shifting with the slow precession of the equinoxes or the wobble of Earth's axis, moving with purpose and with momentum that nothing in the local universe can arrest. The Milky Way is falling. It has been falling for billions of years, and the thing it is falling toward is the other great structure visible in the night sky to anyone who knows where to look, a faint, oval smudge in the constellation Andromeda that requires moderately dark skies to see with the naked eye, but that, once you know it is there, becomes almost impossible not to notice. That smudge is the Andromeda Galaxy. It is the largest member of our local group of galaxies. It contains approximately 1 trillion stars. It spans roughly 220,000 light-years in diameter, making it physically larger than the Milky Way, even if our galaxy may be comparably massive when dark matter is accounted for, and it is falling toward us at 110 kilometers per second, every second of every day, without deviation, without deceleration, locked onto a collision course that was established by the gravitational geometry of the early universe before our Sun had formed, before Earth existed, before any of the atoms in your body had been assembled by the nuclear furnaces of dying stars. In approximately 4.5 billion years, these two structures will collide, and what follows that collision, but what the collision actually is, and what it actually does, and what it leaves behind, is the subject of this exploration. But I want to be precise about what I mean by exploration, because this is not going to be a surface treatment of a dramatic astronomical event. It is going to be a genuine attempt to understand the collision at every level available to us, from the quantum mechanical properties of the matter involved to the large-scale gravitational dynamics of merging dark matter halos to the philosophical implications of what it means for a galaxy to lose its identity, to the strange and irreducible fact that a collision of this magnitude is being contemplated at all, by beings who are made of the very matter that will participate in it. By the time we are done, you will understand why the most common assumption about this collision, the assumption that it will be catastrophic in the obvious, destructive, everything burns sense, is not just wrong, but is wrong in a way that is far more interesting than being right would have been. You will understand what galaxies actually are, not what they look like, but what they are made of, how their matter is distributed, what forces maintain their structure, and why those facts determine everything about how they interact when they meet. You will understand the precise sequence of events that will unfold over the 2 billion years of the merger process, from the first overlap of dark matter halos that is already happening right now, to the final coalescence of 2 supermassive black holes in an event so energetically extreme that it briefly outshines the combined light of every star in the observable universe. You will understand what the merged remnant will look like, how it will behave, and what it means that the specific organizational identities of both the Milky Way and Andromeda will be dissolved completely and irreversibly into something new. And you will understand why, despite the fact that most individual stars survive the merger, despite the fact that the solar system will almost certainly persist through the event, despite the fact that the atoms in your body will still be somewhere in the merged galaxy billions of years from now. The title of this exploration is precisely accurate. Nothing survives, not in the sense that matters most, not the arrangements, not the patterns, not the specific, historically contingent, were improbably beautiful organizations of matter and motion and history that make the Milky Way, and Andromeda, the Andromeda. Those are ending. They are ending slowly, on timescales that dwarf the history of life on Earth, but they are ending as certainly as anything in this universe ends. And understanding why they are ending and what their ending means requires us to go deep into the nature of galaxies, the nature of matter, and the nature of complexity itself. There is one more thing I want to plant in your mind before we begin in earnest. One image, one question that I'm going to ask you to carry with you through everything that follows, and that will not receive its full answer until the very end of this exploration. When you look up at that smear of light in Andromeda, you are looking at something that is 2.5 million light years away. The light reaching your eyes left Andromeda 2.5 million years ago, when our ancestors were small-brained bipeds on the African savanna who had not yet discovered fire. The galaxy you are seeing is not the galaxy as it is the galaxy as it was. And everything we know about it, every measurement we have made, every calculation we have performed, is based on light that is already ancient by the time it reaches us. So here is the question. What is happening in Andromeda right now, at this very moment, as you read these words? We cannot know. We will not know for 2.5 million years. And that unknowability, that fundamental limitation imposed by the finite speed of light, is not just an inconvenience for astronomers. It is a window into something deep about the nature of the universe and our place in it. Hold that question. We will return to it. If you have found this kind of deep, unhurried exploration valuable, taking a moment to share it with someone who thinks carefully about the universe does more to support this work than almost anything else. Now, let us begin at the beginning, which in this case means beginning with what a galaxy actually is. The word galaxy comes from the Greek word for milk, which is galaxious, which is itself derived from gala, The ancient Greeks named the band of light overhead the Milky Circle, and the name stuck through 2.5 millennia of astronomy, and eventually came to denote not just our own band of light, but every similar structure in the universe. There are, by current estimates, somewhere between 2 trillion and 2 trillion galaxies in the observable universe, though that number has been revised upwards several times as our instruments have improved, and our understanding of how many small, faint galaxies existed in the early universe has deepened. 2 trillion is a number so large that it has essentially no intuitive content. It is simply vast in a way that resists comprehension. But a galaxy is not just a large collection of stars. That description is accurate in the way that saying a city is a large collection of buildings is accurate. It captures the most visible feature while missing almost everything important about the structure. A galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas and dust, and an enormous quantity of dark matter, all organized by gravity into a coherent structure that maintains its form over billions of years through a dynamic equilibrium between gravitational attraction and the orbital motions of its components. That is a more complete description, but even it understates the complexity of what a galaxy actually is. Let us take the Milky Way specifically and examine it with the precision it deserves. Our galaxy has several distinct structural components, each with its own physical properties, its own history, its own role in the overall system, and its own fate in the merger event to come. Understanding these components separately is essential before we can understand how they interact with Andromeda's equivalent components during the collision. The first and most familiar component is the thin disk. This is the flat, a rotating structure that contains most of the galaxy's visible stars and virtually all of its star-forming activity. The thin disk of the Milky Way is approximately 100,000 light-years in diameter and somewhere between 1,000 and 2,000 light-years thick, which means its aspect ratio is roughly that of a vinyl record, enormously wide relative to its thickness. The thin disk contains the spiral arms, which are not physical structures in the sense of being made of specific stars that are always in the arms, but are density waves, regions of enhanced stellar and gas density that rotate around the galaxy at a different speed than the individual stars do. Stars and gas clouds enter a spiral arm, spend some time in the denser region, and then emerge on the other side. The arm persisting as a pattern even as its constituent material constantly changes. This is a subtle and important point that we will return to when we discuss how the collision destroys the spiral structure. Within the thin disk, stars are not uniformly distributed. There are regions of higher density, particularly associated with the spiral arms, and regions of lower density between the arms. The spiral arms are also the sites of active star formation because the compression of gas as it enters the denser arm region can trigger the gravitational collapse of gas clouds into new stars. The thin disk is therefore not a static structure, but a dynamic one, constantly forming new stars in its arms. Those stars living out their lives and dying, like the most massive ones exploding as supernovae and enriching the surrounding gas with heavy elements. The enriched gas eventually cooling and collapsing to form the next generation. The thin disk is alive in a way that an elliptical galaxy is not, and that aliveness is one of the things the merger will end. The second major structural component is the thick disk. Less well known than the thin disk, the thick disk is a somewhat more extended and kinematically hotter component of the Milky Way's disk structure, containing older stars that have had their orbits slightly puffed up by billions of years of gravitational perturbations from molecular clouds and satellite galaxy interactions. The thick disk stars are on average older than thin disk stars and are somewhat more metal-poor. Meaning they contain lower abundances of elements heavier than hydrogen and helium because they formed earlier in the galaxy's history when fewer generations of stellar nucleosynthesis had enriched the interstellar medium. The thick disk is a record of the galaxy's earlier evolutionary phases, a fossil population that tells us something about what the Milky Way looked like several billion years ago. The third component is the central bulge. At the center of the Milky Way, the flat disk gives way to a roughly spheroidal concentration of stars that bulges out above and below the plane of the disk. The Milky Way's bulge is not a simple spheroid, however. It has a pronounced bar structure, an elongated concentration of stars running through the galactic center at an angle to our line of sight. This bar is the reason our galaxy is classified as a barred spiral galaxy rather than a simple spiral. The bar plays an important role in the dynamics of the inner galaxy, channeling gas inward toward the galactic center through gravitational resonances. The bulge contains mostly old stars, formed early in the galaxy's history, and has very little ongoing star formation compared to the disk. At the very center of the bulge, at the precise dynamical center of the entire galaxy, sits Sagittarius A star. This is our galaxy's supermassive black hole, a region of space-time where approximately 4 million solar masses of matter have been compressed into a volume smaller than our solar system. We know it is there not because we can see it directly. Black holes, by definition, emit no light of their own, but because we can track the orbits of stars very close to the galactic center and measure the gravitational influence that must be causing those orbits. The stars nearest to Sagittarius A star move at extraordinary speeds, some of them completing full orbits in just a few years, following trajectories that can only be explained by the presence of an extremely massive, compact object at the center of their orbits. The mass of that object, derived from careful measurements of those stellar orbits over decades of observation, is 4.15 million solar masses, with an uncertainty of roughly 1%. 4 million solar masses sounds large, and it is, but it is worth putting in context. The entire Milky Way contains somewhere between 500 billion and 1 trillion solar masses of matter when dark matter is included. And Sagittarius A star, despite being the most massive single object in the galaxy, represents a tiny fraction of the total mass. It matters not because of its mass relative to the galaxy as a whole, but because of its location and the role it plays in the dynamics of the galactic center, and because of what happens when it eventually encounters Andromeda's central black hole, which is dramatically more massive than ours. Beyond the disk and the bulge, the Milky Way has a stellar halo. This is a diffuse, roughly spherical distribution of old stars and star clusters that extends to distances of several 100,000 light-years from the galactic center, well beyond the thin disk in all directions. The stellar halo is sparse, containing only a small fraction of the galaxy's total stars, but it is important as an archaeological record of the galaxy's history. Many of the stars in the halo are extremely old, formed in the earliest epochs of the galaxy's existence, and many of them arrived there, not through formation in the halo, but through the accretion and disruption of smaller satellite galaxies that fell into the Milky Way over billions of years. When a satellite galaxy is torn apart By the tidal forces of the Milky Way, its stars are scattered into streams that wrap around the galaxy in great arcs, and these streams persist for billions of years before fully phase mixing into the smooth background of the halo. The halo is full of these streams, visible to astronomers as slight overdensities in the distribution of halo stars, each one the ghost of a satellite galaxy that no longer exists as a coherent structure. This accretion of smaller galaxies is not just ancient history, it is ongoing. The Large and Small Magellanic Clouds, the two most prominent satellite galaxies of the Milky Way, are currently being tidally disrupted by our galaxy's gravitational field. The Magellanic Stream, a vast ribbon of hydrogen gas stretching across a large portion of the sky, is material being stripped from the Magellanic Clouds by the Milky Way's tidal forces. The clouds themselves are on an orbit that will eventually bring them close enough to the Milky Way to be fully incorporated, adding their stars and gas to our galaxy's inventory. This will happen, according to some models, even before Andromeda arrives, meaning the Milky Way may already be in the process of its last significant minor merger before the major event to come. And then, encompassing all of these visible components, the thin disk and the thick disk and the bulge and the stellar halo and all the satellite galaxies, there is the dark matter halo. This is the dominant structural component of the Milky Way in terms of both mass and spatial extent. And it is the component that is least familiar because it is the component that cannot be seen. The dark matter halo of the Milky Way is roughly spherical, extending to distances of perhaps 600,000 to 1 million light-years from the galactic center. Its total mass is estimated at somewhere between 800 billion and 1 trillion solar masses, compared to the roughly 60 billion solar masses in visible stars. The dark matter outweighs the visible matter by a factor of roughly 15 to 20 when the full halo is considered. We know the dark matter halo exists because of its gravitational effects, the rotation curve of the Milky Way, the way the orbital speeds of stars and gas clouds vary with their distance from the galactic center, does not follow the pattern you would predict if the galaxy's mass were concentrated in its visible components. If the mass were concentrated in the disk and bulge, the rotation curve should fall off at large radii, the way the orbital speeds of planets in the solar system fall off with distance from the Sun. Instead, the rotation curve of the Milky Way stays flat or even rises slightly at large radii, which can only be explained by the presence of additional mass distributed in a large spherical halo around the visible galaxy. That additional mass is the dark matter. Dark matter is one of the most significant open problems in all of physics. We know it exists because of its gravitational effects, not just in the Milky Way, but in thousands of other galaxies, in galaxy clusters, and in the large-scale structure of the universe itself. We know approximately how much of it there is, how it is distributed, and how it behaves gravitationally. What we do not know is what it actually is, what particles make it up, why it does not interact electromagnetically, whether it is a single type of particle or a complex dark sector with its own internal physics, whether it has any interactions with ordinary matter beyond gravity. These questions are among the most actively pursued in experimental physics, with underground detectors, particle colliders, and space-based observatories, all searching for some signal that dark matter leaves in the ordinary matter world. So far, the dark matter has revealed itself only through gravity, and through gravity alone, it has reshaped our understanding of what galaxies are and how they form and evolve. For the purposes of understanding the Andromeda collision, The most important fact about dark matter is its spatial distribution. The Milky Way's dark matter halo extends roughly 10 times farther from the galactic center than the visible disk does. Andromeda's dark matter halo is comparably large, perhaps extending even farther, given Andromeda's somewhat larger total mass. And at the current separation of 2.5 million light-years between the two galaxies, those halos are not yet overlapping significantly. But they are not infinitely far from doing so either. As the galaxies approach over the next 1 to 2 billion years, the halos will begin to interpenetrate long before the luminous disks come anywhere near each other. This is the first and most important structural fact about the collision. It begins not with the dramatic, photogenic interaction of two spiral galaxies, but with the silent, invisible merger of two dark matter halos. The dark matter merger is the foundation on which everything else is built, because the dark matter halo sets the gravitational potential within which all the visible matter moves. As the two halos begin to interact and eventually merge into one combined halo, the gravitational landscape within which the stars and gas of both galaxies orbit will change. And changing gravitational landscapes mean changing orbits, and changing orbits for hundreds of billions of stars in two massive galaxies mean transformations of structure that unfold over billions of years, but are no less real for their slowness. Before the dark matter halos have fully merged, before the first star from Andromeda has crossed into the volume of space we would recognize as the Milky Way's territory, something else is already happening that sets the stage for everything to follow. The two galaxies are not approaching each other in isolation. They are embedded in a gravitational web that connects them to every other member of the local group. And the geometry of that approach, the specific angle and velocity and angular momentum of the encounter will determine almost everything about how the merger unfolds. Understanding that geometry is not a technical detail, it is the difference between a grazing encounter and a direct hit, between a merger that takes 2 billion years and one that takes 3. Between a remnant that retains some faint memory of its disk structure and one that is thoroughly scrambled into a featureless ellipsoid. The geometry of this collision has been measured, and the measurements are precise enough to give us a detailed picture of what is coming. The measurement of Andromeda's motion relative to the Milky Way is one of the great technical achievements of modern observational astronomy. For most of the history of the study of galaxies, astronomers could measure only the radial velocity of Andromeda, meaning the component of its motion directly toward or away from us. This measurement is made through the Doppler shift of Andromeda's light. When a light source moves toward an observer, the wavelengths of its emitted light are compressed, shifting the spectrum toward the blue end. When it moves away, the wavelengths are stretched, shifting the spectrum toward the red. By measuring the precise wavelengths of known spectral lines in Andromeda's light and comparing them to the laboratory wavelengths of those same lines, astronomers can determine how fast the galaxy is moving along our line of sight. This measurement was first made in the early 20th century, and the result was immediately striking. Andromeda showed a blue shift, meaning it was moving toward us. At a time when most astronomers assumed galaxies were essentially stationary or moving slowly, the discovery that Andromeda was approaching at a significant speed was notable. The measured radial velocity has been refined over the decades and now stands at approximately 110 kilometers per second toward us. This is the number you may have encountered in popular accounts of the collision, and it is real and well established, but the radial velocity is only one component of Andromeda's motion. The other component, the transverse velocity, the speed at which Andromeda is moving across our line of sight rather than along it, is much harder to measure. This is because the transverse motion of a galaxy 2.5 million light-years away produces an angular shift on the sky that is extraordinarily small even over long periods of observation. The apparent motion of Andromeda across the sky due to its transverse velocity is measured in micro-arc seconds per year, far below what any ground-based telescope can detect and at the very limit of what the best space-based astrometric missions can achieve. The measurement of Andromeda's transverse velocity was accomplished using the Hubble Space Telescope over a period of many years, tracking the positions of individual stars in Andromeda relative to background galaxies so distant that they can be treated as effectively stationary reference points. The result, published in a landmark paper in 2012, revealed that Andromeda's transverse velocity is significantly smaller than its radial velocity. The most likely value is that Andromeda is moving almost directly toward us, with a transverse velocity component of somewhere around 17 kilometers per second, much smaller than the radial component of 110 kilometers per second. This measurement has profound implications for the nature of the collision. A small transverse velocity means a nearly head-on encounter. The two galaxies are not going to swing past each other in a glancing blow with most of their relative velocity directed across the line of sight. They are coming at each other almost directly, with the bulk of their relative motion aimed straight at the collision. This does not mean the merger will be instantaneous or clean, because even a nearly head-on collision of two extended structures like galaxies involves enormous complexity and takes billions of years to resolve. But it does mean the merger will be more thorough, more complete, and more transformative than a glancing encounter would be. The galaxies will interpenetrate deeply rather than merely grazing each other, and the gravitational interaction will be correspondingly more intense. There is an uncertainty in this measurement that is worth acknowledging honestly. The transverse velocity measurement is at the edge of what current technology can achieve, and the error bars are not negligible. The true transverse velocity could be somewhat larger than the most likely value, which would mean a somewhat less direct encounter. Simulations of the merger have explored a range of possible initial conditions consistent with the measurement uncertainties, and while the details vary, the broad outcome is robust across this range. The galaxies will merge. The merger will produce an elliptical remnant. The specific path they take to that outcome, the exact geometry of the first close approach and subsequent passages varies with the assumed transverse velocity, but the destination is the same. The simulations of the Milky Way Andromeda merger are among the most sophisticated numerical experiments in modern astrophysics. They are run on supercomputers using codes that track the gravitational interactions of millions of particles representing stars and dark matter, following their trajectories through billions of years of simulated time. The most detailed simulations include not just gravity, but also gas dynamics, star formation, supernova feedback, and the effects of active galactic nuclei on the surrounding gas. These simulations cannot track every individual star in both galaxies. There are simply too many of them, but they use statistical sampling techniques to represent the full stellar populations in a computationally tractable way. What these simulations reveal about the sequence of events is worth tracing in detail, because the sequence is not what most people imagine. The collision is not a single event. It is a process with multiple distinct phases, each one transforming the system further and setting the conditions for the next phase. Let us follow the timeline from the present moment to the final settled remnant. Right now, as we have established, the two galaxies are approximately 2.5 million light-years apart and approaching at 110 kilometers per second radially. At this separation, the gravitational interaction between them is real but subtle. The Milky Way's gravity is perturbing Andromeda's motion and vice versa. The satellite galaxies of each system are responding to the combined gravitational field of both galaxies, but the gross structure of each galaxy, its disk, its spiral arms, its star-forming activity, is essentially unaffected by the other galaxy's presence. From a structural standpoint, both galaxies are still themselves, still living their separate evolutionary lives, still forming stars and cycling gas and maintaining the dynamic equilibria that give them their current forms. This situation will persist for roughly another 1 billion years before the interaction becomes significantly more noticeable. During this first billion years, the separation between the galaxies will decrease substantially, and the dark matter halos will begin to overlap at their outermost edges. The gravitational interaction will become stronger as the galaxies approach, accelerating their motion toward each other. The satellite galaxies of each system will begin to feel the gravitational pull of the other main galaxy more strongly. And their orbits will start to be perturbed in ways that will eventually lead some of them to be captured by the other galaxy or flung into intergalactic space. The Large Magellanic Cloud, our most massive satellite galaxy, has a particularly interesting fate in this scenario. Some simulations suggest that the Large Magellanic Cloud may actually collide with the Milky Way before Andromeda arrives. The Large Magellanic Cloud is currently at a distance of roughly 160,000 light-years from the Milky Way and is moving at a speed that suggests it may be on its first close approach to our galaxy rather than a bound orbital companion. Some models indicate it will make a close passage to the Milky Way in roughly 2 billion years, possibly triggering its own miniature version of the events we are describing. With tidal distortion, gas stripping, and a burst of star formation in both systems, this pre-collision with the Large Magellanic Cloud may actually set up the Milky Way's disk in a somewhat different configuration than it is in today, when Andromeda finally arrives, adding another layer of complexity to an already complex situation. But let us stay focused on the main event. Approximately 3 to 4 billion years from now, the separation between the Milky Way and Andromeda will have decreased to the point where the outer edges of the luminous disks begin to feel the gravitational influence of the other galaxy strongly enough to produce visible distortions. The disks will not yet be overlapping. The stars of each galaxy will still be orbiting primarily in their own galactic gravitational potential. But the tidal force of the approaching galaxy will begin to stretch and distort the outer parts of each disk, pulling material toward the oncoming galaxy on the near side and away from it on the far side. This tidal distortion is the first visible sign of the impending encounter. The tidal distortion will produce features that have been observed in many pairs of interacting galaxies throughout the universe. The outer regions of each spiral will be drawn out into elongated streamers and bridges. Stars from the outer disk, which are less tightly bound to the galactic center than stars in the inner disk, will be pulled into extended tidal tails that curve away from the main body of each galaxy in long, graceful arcs. Gas in the outer disk will be similarly distorted, and in some regions the distortion will be enough to trigger local collapses and the formation of new stars in the tidal features themselves. Observers anywhere in the local group with sufficiently advanced telescopes would begin to see the two previously symmetric spirals developing asymmetries and extensions that betray the gravitational interaction driving them. This phase of the interaction, the tidal distortion phase before the disks actually overlap, could last several 100 million years. During this time, the galaxies are still approaching each other, still accelerating under their mutual gravity, but the visible disk structures are already being transformed. The familiar spiral patterns of both galaxies will begin to degrade. The symmetric, the organized spiral arms that we see today in the Milky Way and that astronomers observe in Andromeda's disk will develop kinks and distortions as the gravitational field that maintains their coherence is modified by the approaching companion. Then comes the first close approach. This is the moment that most people imagine when they think of the collision, the moment when the two galaxies pass through each other. But even this framing requires correction, because the galaxies do not so much pass through each other as they interpenetrate and then separate and then fall back together again. The first close approach is not the merger, it is the beginning of a gravitational conversation that will take billions of years to resolve. During the first close approach, the cores of the two galaxies, the densest central regions containing the oldest stars and the supermassive black holes, will pass within perhaps a few tens of thousands of light years of each other, perhaps closer. The exact distance of closest approach depends on the transverse velocity and the precise geometry of the encounter, and the simulations span a range of outcomes. But in the most likely scenarios, the first closest approach brings the cores within a distance comparable to the radius of the disk itself, meaning the disks genuinely overlap in their central regions, rather than merely exchanging tidal forces at their peripheries. During this passage, the gravitational forces experienced by individual stars in both galaxies will change dramatically and rapidly by galactic standards, though slowly by human standards. A star in the outer disk of the Milky Way that is currently orbiting in a well-defined circular orbit at a specific radius will suddenly find itself in a gravitational field that is being significantly modified by the presence of Andromeda's mass distribution passing through the same volume of space. Its orbit will be perturbed. The perturbation may be small, nudging the orbit slightly out of round. It may be large, significantly changing the orbital energy and angular momentum of the star, sending it into a much more elongated orbit that carries it far from its original position before bringing it back. Or, in some cases, the perturbation may be large enough to give the star enough energy to escape the galaxy entirely, sending it into intergalactic space on an unbound trajectory from which it will never return. This last possibility, the ejection of stars into intergalactic space, is one of the most striking consequences of the merger, and one that is most clearly visible in other merging galaxy systems we can observe today. The tidal tails of interacting galaxies contain billions of stars that have been drawn out of the main bodies of the interacting galaxies and flung into extended structures that can span hundreds of thousands of light years. In the most dramatic cases, stars at the tips of these tidal tails are moving fast enough to escape the merged system entirely, becoming intergalactic stars, isolated stellar objects floating in the void between galaxies with no galactic home. The universe contains a significant population of these intergalactic stars detected through surveys of the light between galaxy clusters, where a diffuse glow betrays the presence of stars that belong to no galaxy. These stars are the refugees of past mergers, flung out of their home galaxies by the gravitational chaos of collisions that happened billions of years ago. The Milky Way Andromeda merger will add to this population, contributing some number of stars, perhaps in the tens of billions, to the growing intergalactic stellar field of the local group. But the tidal ejection of stars into intergalactic space is, by the numbers, a relatively minor effect of the merger in terms of the total stellar inventory. The vast majority of stars in both galaxies will remain bound to the merged system, even if their orbits are dramatically altered. The gravitational potential of a system containing 1.3 trillion stars and a combined dark matter halo of roughly 2 trillion solar masses is deep enough to hold onto most of its stellar content through even the most violent gravitational disturbances of the merger. What changes for these retained stars is not whether they are bound, but how they are bound, the shape and orientation and energy of their orbits, which determines the overall structure of the system they collectively inhabit. Now, we need to talk about what happens to the gas, because while the stars behave as collisionless particles, interacting only gravitationally and essentially passing through each other, without direct physical contact, the gas of both galaxies is collisional. Gas molecules and atoms interact electromagnetically. When two clouds of gas meet at high relative velocity, the gas does not pass through itself the way the stars do. It shocks. A shock in a gas is a discontinuity in the flow properties, a surface across which the velocity, density, temperature, and pressure of the gas change abruptly. Shocks form wherever gas is forced to transition rapidly from supersonic to subsonic flow, and they are ubiquitous in astrophysics, occurring in supernova remnants, in the wakes of stars moving through the interstellar medium, in the jets of active galactic nuclei, and, critically, in the collision zones of merging galaxies. When the interstellar gas of Andromeda encounters the interstellar gas of the Milky Way during the first close approach, the collision speed, measured as the full three-dimensional relative velocity of the two galactic disks, all will be several hundred kilometers per second. This is well above the sound speed in the interstellar medium, which is typically a few tens of kilometers per second in the warm, neutral medium, and somewhat higher in the hot, ionized medium. The collision is therefore highly supersonic, and strong shocks will form throughout the interaction region. These shocks do several things. First, they heat the gas. The kinetic energy of the collision is converted into thermal energy as the gas is decelerated across the shock front. Gas that was cold and neutral before the shock can be heated to temperatures of millions of degrees in the post-shock region. This hot gas becomes visible in X-ray wavelengths, glowing with thermal Bremsstrahlung radiation as the electrons and ions in the hot plasma interact. Second, the shocks compress the gas. The density in the post-shock region is higher than in the pre-shock region, sometimes by factors of 4 or more in strong shocks. Third, and most consequentially for the subsequent evolution of the system, the shocks can trigger the gravitational collapse of gas clouds into new stars. Star formation is, at its heart, a competition between gravity and pressure. A gas cloud will collapse to form stars if its self-gravity is strong enough to overcome the thermal pressure that supports it against collapse. This condition is captured in what is called the Jeans criterion, named after the British physicist James Jeans, who derived it in the early 20th century. A cloud of gas will collapse spontaneously if its mass exceeds a critical value, the Jeans mass, which depends on the temperature and density of the gas. The Jeans mass is lower in denser, colder gas and higher in less dense, hotter gas. Shocks increase density and can also cool gas rapidly through radiative processes, both of which tend to lower the gene's mass and make star formation more likely. Shocked gas is therefore primed for star formation in a way that quiescent interstellar gas is not. The star formation triggered by the gas collision during the Milky Way Andromeda merger will be orders of magnitude more intense than anything either galaxy currently experiences. To put this in perspective, consider the current state of star formation in our galaxy. The Milky Way is forming new stars at a rate of roughly 1 to 3 solar masses per year, averaged over the whole galaxy. This modest rate reflects the state of a mature spiral galaxy that has been forming stars for 10 billion years and has used up much of its original gas supply. The gas that remains is distributed in a relatively quiescent interstellar medium, forming stars gradually through the slow compression of molecular clouds by stellar winds, supernova shock waves, and the gentle compression of the spiral density waves. During the merger, this rate will increase by 1 to 2 orders of magnitude. Starburst rates of 50 to several hundred solar masses per year have been measured in other merging galaxy pairs of comparable mass. At the high end, the merger could be forming new stars at a rate 100 times higher than the current Milky Way, converting the equivalent of 100 solar masses of gas into stars every single year. At this rate, a gas reservoir that the current Milky Way could sustain for tens of billions of years would be consumed in hundreds of millions of years. The starburst is a profligate burning through of resources accumulated over billions of years of careful, slow star formation. The starburst will be visually spectacular. The regions of intense star formation will blaze with the blue-white light of massive, short-lived stars. Massive stars, those with masses of 10, 20, 50 or more times the mass of the Sun, burn their hydrogen fuel at prodigious rates and live only a few million years before dying in supernova explosions. A region forming stars at a high rate will therefore be simultaneously brilliant with the light of newly formed massive stars and peppered with supernova explosions, yet each one releasing as much energy as the Sun will emit over its entire 10 billion year lifetime, all in a few weeks. The combined effect of millions of supernovae going off in a relatively compact region over millions of years will drive powerful galactic winds, ejecting gas from the star-forming regions into the extended halo of the galaxy and beyond. Some of this gas will escape the merged system entirely, joining the intergalactic medium. Most of it will eventually fall back, but in a heated, less dense form that is harder to convert into new stars. This feedback from the starburst, the heating and ejection of gas by supernova-driven winds, is one of the mechanisms by which the starburst eventually quenches itself. As the most intense star formation proceeds, the energy input from supernovae heats the surrounding gas, raising the gene's mass and making further star formation harder. The starburst therefore contains the seeds of its own termination. It consumes its fuel rapidly, and the energy it releases in doing so heats and disperses the remaining fuel, ensuring that the episode of intense star formation cannot continue indefinitely. The starburst may last tens to hundreds of millions of years before dying down as the available cold gas is exhausted or heated beyond the point where it can form stars efficiently. But there is another quenching mechanism, one potentially more powerful than supernova feedback alone. The merged supermassive black hole at the center of the new galaxy. As the two galactic cores spiral together and their black holes eventually merge. The merged black hole may become active. accreting the gas that the merger has funneled into the galactic nucleus at a high rate. An actively accreting supermassive black hole, what astronomers call an active galactic nucleus, or a quasar, when particularly luminous, releases enormous amounts of energy in the form of radiation and powerful jets of relativistic plasma. This energy couples to the surrounding gas, heating it to temperatures at which it cannot cool and collapse to form stars. The active galactic nucleus can therefore quench star formation not just in its immediate vicinity but throughout the galaxy, by heating the interstellar medium to the point where it becomes a hot, diffuse atmosphere rather than a cold, clumpy, star-forming reservoir. This process, called AGN feedback, is believed to be one of the primary mechanisms by which massive galaxies become red and dead ellipticals. The merger triggers both the starburst and the AGN activity, and both of these in turn heat and expel the gas that would otherwise fuel future star formation. The result is a galaxy that has used up or expelled most of its cold gas supply and has no efficient mechanism for replenishing it. Star formation drops to a low level and stays there. The galaxy begins its long decline. Let us now follow the merger through its later stages after the first close approach. After the two galactic cores have swung past each other, the system will not immediately coalesce. The two cores will recede from each other. When drawn apart by their residual relative velocity, even as the combined gravitational potential of the merged dark matter halo works to pull them back together. This recession will not bring the cores anywhere near their original separation of 2.5 million light-years. The energy lost to tidal distortions, gas shocks, and the dynamical friction of the dark matter halos will have significantly reduced the total orbital energy of the system. The cores will recede to perhaps a few 100,000 light-years before falling back toward each other for a second close approach. Dynamical friction is a concept worth explaining carefully, because it is one of the most important mechanisms driving the ultimate coalescence of the two galactic cores. When a massive object, like the core of one galaxy, moves through a distribution of other particles like the dark matter particles and stars of the other galaxy, it gravitationally attracts those particles toward it as it passes. The particles are deflected slightly toward the path of the moving object, creating an overdensity of material in the wake of the moving object and a slight underdensity ahead of it. This asymmetric distribution of surrounding material exerts a net gravitational force on the moving object, directed backward along its path, opposing its motion. This retarding force is dynamical friction. Dynamical friction is the mechanism by which satellite galaxies that fall into larger galaxies eventually sink to the center rather than orbiting forever. It is the mechanism by which the two galactic cores of a merging system gradually lose energy to the surrounding stellar and dark matter distributions and spiral toward each other, rather than orbiting each other indefinitely. The efficiency of dynamical friction depends on the density of the medium through which the object is moving and the mass of the object itself. In the dense central regions of the merged galaxy, where the stellar and dark matter densities are high, dynamical friction operates efficiently, and the two cores will spiral together on timescales of hundreds of millions to a few billion years. The second close approach will be more violent than the first in some respects, because by that time the two galactic disks will be even more thoroughly interpenetrating and the relative geometry will be different. Additional tidal distortion, additional gas shocking, and additional star formation will occur. The cores will again swing past each other, again recede, and again fall back together. Simulations typically show 2 to 4 such passages before the cores finally merge into one. Each passage dissipates more energy, each recession is shorter, and each subsequent approach is more direct. The system is converging on coalescence through a process of ever-tightening orbital decay. During all of these passages, the stellar populations of both galaxies are being scrambled. Stars that were neatly organized in circular orbits in a flat disk are being scattered into elongated, tilted, randomly oriented orbits by the gravitational perturbations of the merger. The disk structure of both galaxies is being progressively destroyed, not in one cataclysmic moment, but gradually, passage by passage, perturbation by perturbation. The cold, organized, rotation-dominated kinematics of a spiral galaxy's disk is being replaced by the hot, disordered, pressure-supported kinematics of an elliptical galaxy's stellar body. The transition from rotation-dominated to pressure-supported is a fundamental change in the character of the system. In a spiral galaxy, the stars in the disk are supported against gravitational collapse primarily by their rotation. They orbit the galactic center at speeds that balance the gravitational pull inward, much as the Earth orbits the Sun at a speed that balances the Sun's gravitational attraction. Remove the rotation, and the disk would collapse. In an elliptical galaxy, the stars are supported against collapse not primarily by rotation, but by their random motions in 3 dimensions. The elliptical galaxy is not a rotating disk, but a supported cloud, held up by the kinetic energy of its stars moving in all directions. This transition from rotation to pressure support is what happens to the stellar content of the 2 spiral galaxies as the merger proceeds, and it is a transition that cannot be reversed. Once the ordered rotation of the disk is scrambled by the gravitational chaos of the merger, there is no mechanism to restore it. The entropy has increased irreversibly. This irreversibility is worth dwelling on because it connects the astronomical story we are telling to a much deeper story about the direction of time and the tendency of physical systems to evolve from ordered to disordered states. The second law of thermodynamics, the principle that entropy in a closed system tends to increase with time, is operating here on a galactic scale. The 2 organized, low-entropy spiral galaxies are a more ordered state than the one disordered, high-entropy elliptical galaxy they will become. The merger is a thermodynamic process, an increase in entropy written in billions of stars across hundreds of thousands of light-years. The universe is doing what the universe always does, which is to move from order toward disorder, from structure toward uniformity, from the improbable toward the probable. And yet, embedded within this overall tendency toward disorder, the merger also creates pockets of extraordinary order. The starburst produces new stars which are extraordinarily complex, the ordered structures compared to the diffuse gas clouds they form from. Those stars may have planets, and those planets may develop chemical complexity, and that chemical complexity may eventually produce life and minds, which are among the most ordered structures in the known universe. The increase in entropy at the galactic scale is consistent with, and indeed enables, the production of extraordinary local order at smaller scales. This is the fundamental paradox of complexity in a universe governed by the second law. The universe tends toward disorder overall, but in doing so it creates, in local regions, transient pockets of order that are more complex and more improbable than anything that could have existed before the disorder-generating process began. The supermassive black holes deserve their own extended treatment, because what happens to them during the merger is not a footnote to the larger story, but one of its most profound and consequential chapters. We have established that the Milky Way harbors Sagittarius A star, a black hole of 4 million solar masses, and that Andromeda harbors a central black hole of somewhere between 100 million and 200 million solar masses. These are not comparable objects. The mass ratio between them is somewhere between 25 to 1 and 50 to 1, meaning Andromeda's black hole is so much more massive than ours that the merger of the two will be thoroughly asymmetric in character, dominated by the dynamics of the more massive object rather than representing an equal partnership between two similar systems. Before we trace the fate of these two black holes through the merger, we need to understand what they are and how they came to be so massive, because the origin of supermassive black holes is itself one of the deepest unsolved problems in astrophysics, and understanding it illuminates something important about the relationship between galaxies and the black holes at their centers. A black hole is a region of space-time where the gravitational field is so strong that the escape velocity exceeds the speed of light. Nothing that enters the region inside the event horizon, the boundary of no return, can escape. Not matter, not radiation, not information in any form we currently understand. The event horizon of Sagittarius A star, with its mass of 4 million solar masses, has a radius of approximately 12 million kilometers. For comparison, the Sun's radius is approximately 696,000 kilometers, meaning the event horizon of our central black hole is roughly 17 times larger than the Sun. But packed into that volume is 4 million times the Sun's mass, at a density so extreme that ordinary physical intuitions about matter and space break down entirely. Black holes of stellar mass, those with masses of a few to a few tens of solar masses, form when massive stars exhaust their nuclear fuel and their cores collapse. If the core mass exceeds a certain threshold, the collapse cannot be halted by any known form of pressure: electron degeneracy pressure, neutron degeneracy pressure, or any other mechanism, and the core collapses to a singularity, a point of infinite density surrounded by an event horizon. The resulting black hole has a mass comparable to the original stellar core, perhaps a few solar masses to a few tens of solar masses. Supermassive black holes with masses of millions to billions of solar masses cannot form this way. No star massive enough to produce a 4 million solar mass core through direct collapse has ever existed. The origin of supermassive black holes is therefore a separate and still actively debated question. The leading scenarios involve the formation of massive seed black holes in the early universe, either through the direct collapse of massive gas clouds in the first billion years after the Big Bang, or through the rapid merging of stellar mass black holes in the dense star clusters that formed in the earliest galaxies, done followed by billions of years of growth through accretion of surrounding gas and through mergers with other black holes during galaxy mergers. The growth of supermassive black holes through mergers is particularly relevant to our story. Every time two galaxies merge, their central black holes eventually merge as well, and the merged black hole is more massive than either of its progenitors. Over cosmic time, as galaxies have grown through a hierarchical sequence of mergers, their central black holes have grown alongside them. The most massive black holes in the universe, the ultramassive black holes with masses of tens of billions of solar masses, found at the centers of the largest elliptical galaxies in galaxy clusters, are believed to have grown to their current masses through exactly this process. On accumulating mass through both gas accretion during active phases and black hole mergers during galaxy mergers. Andromeda's black hole at 100 to 200 million solar masses is already a product of this process, having grown through the merger history of Andromeda itself. The Milky Way's black hole at 4 million solar masses is relatively modest by the standards of massive galaxies, which may reflect a quieter merger history for our galaxy compared to Andromeda. When the merger of the Milky Way and Andromeda begins in earnest, the two black holes will initially be separated by distances comparable to the separation between the galactic cores, which may be tens of thousands of light years at the time of first close approach. At this separation, the two black holes are not yet a gravitationally bound pair. They are simply the central mass concentrations of their respective galaxies, each embedded in its own dense stellar nucleus, each surrounded by its own accretion disk if gas has been funneled to the center, and each moving relative to the other in response to the overall gravitational dynamics of the merger. As the galactic cores spiral together under dynamical friction, the two black holes will be carried along with them, gradually approaching each other. The stellar nuclei surrounding each black hole, the dense concentrations of old stars that cluster around the galactic center, will interact with each other as the cores merge, and this interaction will further concentrate mass toward the center of the merged system, creating conditions favorable for the black holes to eventually form a gravitationally bound binary. The formation of the black hole binary is expected to occur when the two black holes are separated by roughly 1 parsec, which is approximately 3.26 light years. At this separation, the gravitational binding energy of the binary exceeds the kinetic energy of the surrounding stellar environment, and the two black holes begin to orbit each other as a true gravitationally bound pair rather than as two independent objects moving in the same gravitational potential. What happens next has been one of the most discussed problems in theoretical astrophysics for decades. It is called the final parsec problem, and it refers to the difficulty of getting the two black holes from a separation of 1 parsec to a separation close enough that gravitational wave emission can drive them to merger in a reasonable amount of time. The issue is this: as the black hole binary forms and begins to harden, meaning its orbital separation decreases and its binding energy increases, it does so initially by ejecting stars from the surrounding stellar cusp through gravitational slingshot interactions. A star that passes close to the black hole binary can interact with both black holes in a three-body encounter, gaining kinetic energy at the expense of the binary's orbital energy. The star is flung out at high speed, the binary's orbit shrinks slightly, and the process repeats with the next star. This mechanism is efficient when there is a plentiful supply of stars on orbits that bring them close to the binary. But as stars are ejected, they are replaced by stars coming in from larger radii on orbits that are not necessarily well aimed at the binary. In a spherically symmetric stellar system, once the initial supply of stars on loss cone orbits, meaning orbits that bring them close to the binary, is depleted, the replenishment rate may be too slow to drive the binary to merger within the age of the universe. This is the final parsec problem. The binary may stall at a separation of roughly 1 parsec and remain there, orbiting each other indefinitely without shrinking further. However, the final parsec problem is primarily a concern for idealized, spherically symmetric stellar systems. In the messy, asymmetric, gas-rich environment of a galaxy merger, the situation is likely very different. The merger itself creates non-spherical stellar distributions, triaxial potentials, and streams of stars on orbits that cross the center of the merged system at rates much higher than in a relaxed, symmetric system. Gas funneled to the center by the merger can form a circumbinary disk around the black hole binary, and the torques from this disk can drive the binary to smaller separations efficiently. The merger-driven asymmetries in the stellar distribution continuously replenish the loss cone of stellar orbits, providing a steady supply of stars to be ejected and driving continued hardening of the binary. Most current theoretical work and numerical simulations suggest that in the context of real galaxy mergers, the final parsec problem is not actually a problem, that the binary does continue to harden and eventually reaches separations where gravitational wave emission takes over as the dominant energy loss mechanism. The timescale for this process in the Milky Way Andromeda merger is uncertain, but estimates range from a few 100 million years to perhaps 1 billion years after the cores merge, which is a long time by human standards, but a small fraction of the total merger timescale. Once the black hole binary reaches a separation of roughly 1,000th of a parsec, the power radiated in gravitational waves becomes comparable to the power lost through stellar ejection, and gravitational wave emission becomes the dominant driver of the orbital decay. From this point, the merger proceeds inexorably. Gravitational waves carry energy and angular momentum away from the binary at an increasing rate as the separation decreases, and the decreasing separation leads to more gravitational wave emission in a runaway process that ends only when the two black holes merge into one. The final in spiral. From the point where gravitational waves take over to the actual merger is extraordinarily rapid by astronomical standards. The binary will spend most of its time at relatively large separations where the gravitational wave power is modest, but as the separation shrinks below a certain threshold, the inspiral accelerates dramatically. The final few orbits, from a separation of perhaps a few astronomical units down to merger, may take only a few months to a few years of real time. After billions of years of slow approach and orbital decay, the actual coalescence of the two black holes is almost instantaneous. The gravitational waves emitted during the final inspiral and merger of two black holes with a combined mass of 100 to 200 million solar masses will be among the most powerful gravitational wave sources in the universe. The frequency of these waves will be in the nanohertz to microhertz range, far below the frequency range detectable by ground-based gravitational wave detectors like the Laser Interferometer Gravitational Wave Observatory, which is sensitive to waves in the frequency range of tens to thousands of hertz. But a space-based gravitational wave detector with arm lengths of millions of kilometers, like the Laser Interferometer Space Antenna, which is currently planned for launch in the coming decades, would be sensitive to exactly the frequency range of gravitational waves from supermassive black hole mergers to down, and pulsar timing arrays, which use the precise timing of millisecond pulsars as natural gravitational wave detectors, are already sensitive to the background of gravitational waves produced by the population of merging supermassive black hole binaries throughout the universe. In fact, the first evidence for this gravitational wave background from supermassive black hole mergers was reported in 2023, when multiple pulsar timing array collaborations announced correlated timing variations in the millisecond pulses they had been monitoring for years, variations consistent with the expected signature of a stochastic gravitational wave background from the cosmic population of merging supermassive black hole binaries. This is, in a very real sense, The universe announcing the existence of events like the one we are describing. Every time two massive galaxies merge and their central black holes coalesce, the gravitational wave signal from the merger propagates outward at the speed of light, eventually reaching detectors anywhere in the universe sensitive enough to measure it. The gravitational wave signal from the Milky Way Andromeda black hole merger, when it occurs in several billion years, will propagate outward in all directions at the speed of light, carrying information about the masses and spins of the merging black holes encoded in the detailed shape of the wave. If any civilization anywhere within roughly 1 billion light-years of the merger exists and has built a gravitational wave detector, at the time the signal arrives, they will detect it. The merger will announce itself to the universe through the language of space-time distortion, a message written in the geometry of reality itself and transmitted at the maximum possible speed. After the merger, the single combined black hole will settle into a new equilibrium state. The merger of two black holes is not perfectly efficient in terms of converting mass to gravitational waves. Some fraction of the total mass of the binary is radiated away as gravitational waves during the final merger, typically a few percent. The exact fraction depends on the masses and spins of the two black holes. For a merger between a 4 million solar mass black hole and a 150 million solar mass black hole, the total mass radiated as gravitational waves might be a few million solar masses. A prodigious amount of energy, but a small fraction of the total mass. The merged black hole will have a mass of roughly 150 to 200 million solar masses, the sum of the two progenitors minus the radiated fraction. The merged black hole will also receive a gravitational wave recoil kick, a velocity imparted to the merged object by the asymmetric emission of gravitational waves during the final moments of coalescence. Gravitational waves carry not just energy but also linear momentum, and if the emission is not perfectly symmetric, the merged black hole will be kicked in the direction opposite to the net momentum carried by the gravitational waves. The magnitude of this kick depends strongly on the spins of the merging black holes and their orientations relative to the orbital angular momentum. For equal mass mergers with particular spin configurations, the recoil kick can reach thousands of kilometers per second, enough to eject the merged black hole from the galaxy entirely. For unequal mass mergers like the Milky Way Andromeda black hole binary, the recoil kicks are generally smaller because the asymmetry in the gravitational wave emission tends to be less extreme. Most estimates for the recoil kick in this mass ratio regime give velocities of tens to hundreds of kilometers per second, which is well below the escape velocity from the center of the merged galaxy. The merged black hole will therefore remain at or near the center of the new elliptical galaxy, settling back to the center after a brief period of oscillation driven by the kick velocity. It will become the engine at the heart of Milkomeda, potentially fueling a period of active galactic nucleus activity as it accretes the gas funneled to the nucleus by the merger. This active phase of the merged black hole is worth contemplating in detail because it represents one of the most energetically extreme environments in the universe and one that will have profound consequences for the subsequent evolution of the merged galaxy. When a supermassive black hole accretes gas at a high rate, the gas forms a rotating accretion disk around the black hole. As material in the disk loses angular momentum through viscous processes and magnetic instabilities, it spirals inward toward the black hole, releasing gravitational potential energy as heat. The temperature of the inner accretion disk can reach millions to tens of millions of degrees Kelvin, causing it to radiate predominantly in X-rays. The total luminosity of a rapidly accreting supermassive black hole can reach or exceed the Eddington luminosity, which is the theoretical maximum luminosity at which radiation pressure on the surrounding gas balances the inward gravitational force. For a black hole of 150 million solar masses, the Eddington luminosity is approximately 2 times 10 to the power of 47 ergs per second. To put that number in perspective, the total luminosity of the Milky Way in all wavelengths of light is approximately 4 times 10 to the power of 43 ergs per second. A black hole accreting at the Eddington rate would therefore outshine the entire galaxy by a factor of roughly 5,000. This is the luminosity of a quasar, and it is why quasars, which are active galactic nuclei powered by rapidly accreting supermassive black holes, are the most luminous persistent objects in the universe. Whether the merged black hole in Milky will actually reach the Eddington luminosity depends on how much gas the merger funnels to the galactic nucleus and how efficiently that gas can lose angular momentum and reach the black hole. In gas-rich mergers, which the Milky Way Andromeda merger may be to some degree, depending on how much gas remains in both galaxies by the time the merger reaches its final stages, substantial accretion is likely. The resulting active galactic nucleus may shine as a luminous quasar for tens of millions of years before the gas supply in the nucleus is exhausted and the accretion rate drops. The radiation from this quasar phase will have consequences for the entire merged galaxy. The intense radiation field from the nucleus will ionize the surrounding gas, heating it and driving powerful radiation-driven winds that can sweep gas outward from the galactic center on scales of tens of thousands of light years. The mechanical energy from any relativistic jets launched by the black hole will couple to the hot gas of the galactic halo, heating it further and preventing it from cooling and falling back to the disk to fuel future star formation. The combined effect of radiation and mechanical feedback from the active galactic nucleus is one of the primary mechanisms by which massive galaxies become quenched, their star formation shut down and their gas supply heated and dispersed. Or the quasar phase of Milky's central black hole will therefore be one of the final nails in the coffin of the merged galaxy's star-forming career. Already diminished by the consumption of cold gas in the starburst, already heated by the supernova feedback from that starburst, the remaining gas supply of the merged galaxy will be further depleted and heated by the active galactic nucleus. By the time the quasar phase ends and the black hole settles into a quiescent state, accreting at a low rate from the diffuse hot gas of the galactic halo, the merged galaxy will have largely completed its transition from a star-forming spiral system to a red and dead elliptical. What does the elliptical remnant actually look like? This is worth describing in concrete terms. But because the visual impression of an elliptical galaxy is almost the polar opposite of a spiral galaxy, and the contrast illuminates just how complete the transformation wrought by the merger really is. A spiral galaxy like the Milky Way or Andromeda, seen from outside, is a flat, disc-shaped structure with a bright central bulge and sweeping spiral arms traced by young blue-white stars and glowing pink star-forming regions. It has structure at every scale, from the large-scale spiral pattern down to individual star clusters and nebulae. It is visually complex, asymmetric in detail and alive with activity. The blue light of its spiral arms signals ongoing star formation. The pink glow of its emission nebulae signals the presence of hot, young stars ionizing the surrounding gas. The dark lanes of its dust clouds signal the raw material from which future generations of stars will form. An elliptical galaxy is none of these things. It is a smooth, featureless, roughly ellipsoidal blob of light, brighter at the center and fading gradually toward the edges with no sharp boundaries, no spiral structure, no dust lanes, no star-forming regions. Its color is a warm yellow-red, the color of old, low-mass stars that have been burning their hydrogen fuel slowly for billions of years and will continue to do so for billions more. There are no young blue stars because there is no star formation to create them. There are no emission nebulae because there are no hot, young stars to ionize the gas. There are no dust lanes because the dust has been consumed, dispersed, or incorporated into the stellar populations over billions of years of evolution. The internal kinematics of an elliptical galaxy reflect its disordered stellar orbits. Spectroscopic observations of elliptical galaxies show that the stars within them are moving in all directions, with velocity dispersions, meaning the spread in stellar velocities along any line of sight, that are much higher than in the disks of spiral galaxies. The stars in an elliptical are not all rotating in the same direction and the same plane, as disk stars do. They are moving in a three-dimensional distribution of orbits that collectively produce the smooth, spheroidal appearance of the galaxy. Some ellipticals show net rotation, meaning more stars are moving in one direction than another. But the rotation is typically slow, and the galaxy is primarily pressure-supported rather than rotation-supported. Milkomeda will be an elliptical galaxy of significant size. Merging two large spirals produces a large elliptical, and the Milky Way and Andromeda are among the two largest members of the local group. The resulting merger product will have a total stellar mass comparable to the sum of the two parent galaxies, reduced by however many stars are flung into intergalactic space during the merger, which may amount to 10 to 20% of the total stellar inventory. Milkomeda will therefore contain somewhere around 1 to 1.2 trillion stars in its final settled state, making it a fairly massive elliptical by the standards of the local universe. It will sit at the gravitational center of the local group, which by that time will have changed significantly from its current configuration. Most of the smaller member galaxies of the local group will have merged with either the Milky Way or Andromeda, or with each other, or will have been flung out of the group by gravitational interactions during the main merger event. The local group of today, with its 80-odd member galaxies distributed over a volume several million light-years across, will have consolidated into a much smaller number of massive systems centered on the Milkomeda remnant. The Triangulum galaxy, also known as Messier 33, is the third largest member of the local group after the Milky Way and Andromeda. It is a smaller spiral galaxy, currently located approximately 3 million light-years away. Its fate in the merger scenario is uncertain. Some simulations suggest it will be captured by the Andromeda Milky Way system and eventually merge with Milkomeda. Others suggest it may survive as an independent system for much longer, its smaller mass making it less susceptible to tidal capture than a larger galaxy would be. The details depend sensitively on Triangulum's current velocity relative to the local group center of mass, which is not as well measured as Andromeda's velocity. What about the broader cosmological context? The local group is not an island, it is embedded in the larger structure of the universe, which on the scales of hundreds of millions of light years consists of filaments and sheets of galaxies surrounding vast, nearly empty voids. The local group is part of the Virgo supercluster, a large-scale structure centered on the Virgo cluster of galaxies roughly 50 million light-years away. The Virgo cluster contains more than 1,000 galaxies in a volume only a few million light-years across, and its gravitational influence extends outward to affect the motions of galaxies throughout the supercluster, including the local group. However, the local group is not gravitationally bound to the Virgo cluster. It is moving away from the Virgo cluster as part of the general cosmic expansion, though slightly more slowly than a truly isolated group would be due to the gravitational attraction of the Virgo cluster. On timescales of billions of years, the local group will continue to move away from the Virgo cluster, pulled apart by the accelerating expansion of the universe driven by dark energy. Dark energy, the mysterious component of the universe that is causing the expansion of space to accelerate rather than decelerate, is an important part of the context for the Andromeda collision. On the scale of the local group, dark energy is negligible. The gravitational binding of the local group is strong enough to hold it together against the expansive effect of dark energy, and the Milky Way Andromeda merger will proceed regardless of what dark energy does to the universe on larger scales. But on the scale of galaxy clusters and superclusters, dark energy is already dominant. Galaxies in different clusters are being pushed apart by the accelerating expansion, and over tens of billions of years, the universe will become increasingly desolate as the space between gravitationally bound structures grows ever larger. This is the cosmological context within which the Andromeda merger takes place. Not a static universe of stable galaxies, but a dynamic, expanding universe in which gravitationally bound systems like the local group are becoming increasingly isolated islands in an ever larger sea of empty space. The merger of the Milky Way and Andromeda is therefore not just a local event, but part of a larger story about the ultimate fate of matter in an accelerating universe. As the expansion continues and gravitational structures become more isolated, the opportunities for mergers between different groups of galaxies diminish. The mergers happening today and in the near cosmological future are, in some sense, on the last great mergers available to the matter in our region of the universe before the accelerating expansion pulls potential merger partners beyond the reach of gravity forever. On timescales of tens of billions of years, the local group, having consolidated into Milkomeda and perhaps a few other remnant systems, will become an increasingly isolated island. The nearest galaxy clusters, already tens of millions of light-years away, will recede to hundreds of millions and then billions of light-years as the expansion accelerates. The night sky of Milkomeda, already very different from the night sky of the Milky Way today, will become progressively emptier of external galaxies as the recession velocities of distant galaxies eventually exceed the speed of light, and those galaxies disappear beyond the cosmological horizon, the boundary beyond which light can never reach us because the space between us and those galaxies is expanding faster than light can cross it. This is perhaps the most profound long-term consequence of dark energy for our cosmic neighborhood. Not the destruction of the local group, which dark energy cannot accomplish, but the increasing isolation of the local group from the rest of the universe. Milkomeda will eventually be surrounded by empty space on all scales accessible to light, the sole survivor of the local group's consolidation, burning through its remaining stellar fuel in a universe that appears, from the inside, to contain only itself. The stars of Milkomeda will not all die at the same time. This is an obvious statement when written plainly, but its implications for the long-term future of the merged galaxy are worth following carefully, because the stellar population of an elliptical galaxy is not a uniform collection of identical objects aging in lockstep. It is a complex mixture of stars spanning a wide range of masses, luminosities, temperatures, and lifetimes, each on its own evolutionary trajectory, each contributing differently to the overall character of the galaxy at different times. Understanding how this population evolves over tens and hundreds of billions of years is essential to understanding what Milkomeda ultimately becomes, which is in turn essential to understanding the full meaning of what the merger has done. Stars exist on a fundamental trade-off between mass and longevity. Massive stars, those with masses of 10, 20, 50, or 100 times the mass of the Sun, burn their hydrogen fuel at rates so prodigious that they exhaust their core hydrogen supply in only a few million years. They live brilliantly and briefly, blazing as blue or blue-white supergiants of extraordinary luminosity, before dying in supernova explosions that seed the surrounding interstellar medium with the heavy elements their cores have forged. Low-mass stars, those with masses less than the Sun, burn their hydrogen fuel at such modest rates that they can sustain nuclear fusion for tens of billions, hundreds of billions, or in the case of the very lowest mass red dwarf stars, trillions of years. That they live dimly and almost forever on the scale of the current age of the universe, red and cool and extraordinarily long-lived. The starburst triggered by the Andromeda merger will produce stars across this full range of masses, following what astronomers call the initial mass function, the statistical distribution of stellar masses that results from the gravitational fragmentation of a collapsing gas cloud. The initial mass function is a power law, meaning that for every massive star formed, many more lower mass stars are formed, the number of stars increasing steeply as mass decreases. The starburst will produce some number of very massive stars, blazing and brief, but it will produce far more intermediate mass stars and far more again of low mass stars. The massive stars will die within a few million years of the starburst, contributing their supernova energy to the heating and dispersal of the remaining gas and seeding the merged galaxy's interstellar medium with a fresh infusion of heavy elements. The intermediate mass stars, those with masses of a few solar masses, will die over timescales of hundreds of millions to a few billion years, eventually swelling into red giants and shedding their outer layers as planetary nebulae, leaving behind white dwarf remnants. The low-mass stars will live on essentially indefinitely, burning their hydrogen fuel at miserly rates for timescales that dwarf the current age of the universe. The consequence of this mass-dependent lifetime is a predictable evolution in the color of Milkomeda over time. Immediately after the starburst, the merged galaxy will be flooded with the blue-white light of massive, newly formed stars. The starburst population will make Milkomeda briefly bluer and more luminous than it will ever be again. But the massive stars die quickly, and as they do, the average color of the surviving stellar population shifts. The intermediate mass stars evolve off the main sequence and become red giants, contributing a reddish hue. Eventually, as billions of years pass and successive cohorts of stars exhaust their fuel and die, the surviving population becomes increasingly dominated by low-mass, long-lived stars that are intrinsically red and dim. The galaxy reddens and dims progressively, losing luminosity not through any catastrophic event, but through the simple, relentless process of stellar aging. This spectral evolution of elliptical galaxies from the bluer colors of recent star formation toward the redder colors of an aging population has been observed in the populations of elliptical galaxies throughout the universe. When astronomers study elliptical galaxies at different distances and therefore at different look-back times in the history of the universe, they see exactly this pattern. Ellipticals at large distances, observed as they were when the universe was younger, tend to be somewhat bluer than nearby ellipticals, reflecting the fact that their stellar populations were younger and therefore contained more massive, shorter-lived, bluer stars at the time their light was emitted. Nearby ellipticals, observed as they are today, are redder and their stellar populations older. The trend is consistent with a picture in which elliptical galaxies formed the bulk of their stars early in the universe's history during merger-triggered starbursts, and have been slowly aging and reddening ever since. Milky will follow this same evolutionary trajectory. It will be born blue from its starburst, redden over billions of years as its massive and intermediate mass stars die and eventually settle into the deep red glow of a purely old stellar population dominated by low-mass, long-lived stars. The timescale for this color evolution is billions to tens of billions of years. 10 billion years after the merger is complete, Milky will be significantly redder and dimmer than it was during the starburst. 50 billion years after the merger, it will be very much redder and dimmer still. 100 billion years after the merger, most of the stars that contributed significantly to its luminosity immediately after the merger will have died, and the surviving population will consist primarily of the dim, red, low-mass stars that will continue burning for trillions of years. The white dwarfs left behind by the dying intermediate mass and low-mass stars will accumulate in the merged galaxy over time. A white dwarf is the electron-degenerate remnant of a star that has shed its outer layers through stellar winds and planetary nebula ejection and left behind the hot, dense, degenerate core. White dwarfs are typically about the size of Earth and have masses of roughly half a solar mass, to somewhat above the Chandrasekhar limit of 1.4 solar masses, above which electron degeneracy pressure can no longer support the object against gravitational collapse, and the white dwarf will undergo a thermonuclear explosion, a Type 1a supernova. White dwarfs cool slowly over billions of years, radiating away their stored thermal energy. A newly formed white dwarf is hot and bright, glowing blue-white. Over billions of years it cools to yellow, then orange, then red, and eventually, on timescales of many tens of billions of years, to temperatures too low to emit visible light, becoming a black dwarf, a cold, dark, dense remnant of a once active stellar life. Milky will accumulate a growing population of these cooling white dwarfs over its lifetime. The white dwarfs from the starburst generation of stars will be among the first to cool significantly, and over tens of billions of years, the galaxy's stellar inventory will shift from being dominated by actively burning main sequence stars to being increasingly populated by stellar remnants of various kinds. White dwarfs, its neutron stars left behind by the supernova deaths of massive stars, and stellar mass black holes formed from the most massive stellar progenitors will all accumulate in the merged galaxy, their numbers growing as successive generations of stars complete their lives. The neutron stars and stellar mass black holes are particularly interesting because of the possibility of compact object mergers. When two neutron stars orbit each other in a binary system, they lose energy to gravitational wave emission over time and eventually merge. Neutron star mergers are the source of the heaviest elements in the universe, the gold, platinum, uranium, and other elements heavier than iron that cannot be produced in supernova explosions but require the extreme densities and neutron fluxes available in the merger of two neutron stars. These mergers are called kilonovae, are extraordinarily luminous in certain wavelengths and are powerful sources of gravitational waves. Milky will experience numerous kilonova events over its lifetime, each one briefly blazing and then fading, each one enriching the interstellar medium with a fresh supply of heavy elements. But here is something important about those heavy elements. By the time Milky's stellar populations are old enough for significant numbers of neutron star binaries to have inspiraled and merged, the galaxy's ability to incorporate those heavy elements into new stars will be severely limited. The gas supply from which new stars could form will have been largely exhausted by the starburst. The heavy elements produced by late kilonova events will be expelled into the hot, diffuse gas of the galactic halo, where they will reside for enormously long times without being incorporated into new stellar systems. The chemistry of the universe will continue to advance in Milky's halo, the heavy element inventory growing, the composition becoming ever more complex, but with no efficient mechanism to concentrate and cool that enriched gas into stars and planets, the chemical complexity will accumulate without finding expression in new worlds. This is one of the subtler ways in which the merger ends something important. The Milky Way today is a system in which the chemical products of stellar nucleosynthesis are efficiently recycled into new generations of stars and planets. Supernova, ejector, cool and condense and are incorporated into molecular clouds that collapse into new stars. Those stars having planetary systems formed from material enriched by all the previous generations of stellar processing. The chemical complexity of the universe is not just accumulating in diffuse gas, but is being concentrated and structured into planets and potentially into the chemistry of life. Milky, with its exhausted cold gas supply and its hot, diffuse halo, will be far less efficient at this recycling. The heavy elements it produces will mostly go into the halo, and the halo will grow chemically richer over time, but without the cold, dense phase of matter that allows chemistry to build toward genuine complexity. That richness will remain largely unexpressed. Unless the low-mass stars of Milky, the red dwarfs that will burn for trillions of years, provide a new context for complexity. Red dwarf stars, those with masses below roughly 40% of the Sun's mass, are the most common stars in the universe, making up perhaps 70 to 80% of all stars by number. They burn their hydrogen fuel so slowly that the least massive of them will not exhaust their fuel for 10 trillion years or more than 700 times the current age of the universe. They are small, dim, and cool, with surface temperatures of 2,000 to 4,000 degrees Kelvin compared to the Sun's 5,778 degrees Kelvin. Their low luminosity means that any planets in their habitable zones, the regions at the right distances from the star for liquid water to exist on the surface, must orbit very close to the star. Red dwarf planets in the habitable zone face significant challenges for life as we know it. Their close orbital distances make them susceptible to tidal locking, meaning one hemisphere of the planet always faces the star, and the other always faces away, creating extreme temperature contrasts. Red dwarf flares, powerful eruptions of radiation and energetic particles from the stellar surface, can be intense and frequent, potentially stripping the atmospheres of close-in planets or irradiating their surfaces with harmful radiation. But these challenges are not necessarily insurmountable. Models of tidally locked planets suggest that atmospheric circulation can distribute heat from the day side to the night side, maintaining temperatures moderate enough for liquid water over at least part of the surface. And life on Earth has demonstrated a remarkable ability to find and inhabit extreme environments, from deep-sea hydrothermal vents to Antarctic ice to the stratosphere, suggesting that the specific form of challenge posed by red dwarf planets is not automatically a barrier to life. The red dwarf stars of Milky will be the last stars burning in the merged galaxy. Long after the sun-like stars have evolved into red giants and shed their outer layers and left behind cooling white dwarfs, long after the intermediate mass stars of the starburst generation have completed their lives, the red dwarfs will still be burning. They will be the sole source of light and energy in the merged galaxy for trillions of years. Their combined luminosity dimmer than the current Milky Way, but real and potentially sufficient to sustain whatever chemistry or complexity their planetary systems may harbour. If life exists anywhere in the merged galaxy during this long, dim future, it will almost certainly be on planets orbiting red dwarf stars, and the timescales available to that life are almost incomprehensibly vast. A civilization that arose on a red dwarf planet 1 trillion years from now, if such a thing is possible, would inhabit a cosmos profoundly different from the one we inhabit today. The observable universe would be nearly empty of all but the closest, gravitationally bound structures, every other galaxy having receded beyond the cosmological horizon. The cosmic microwave background, the afterglow of the Big Bang that pervades the universe today, would have been redshifted to wavelengths, so long as to be undetectable with any conceivable technology. The universe would be cold and dark and vast, with only the faint red glow of the remaining low-mass stars to illuminate the darkness. And those beings, if they existed, and if they wondered, would have almost no way of knowing what the universe had once been like, how bright and hot and active and full of structure the early cosmos was. They would see only the fading embers of a fire whose peak had passed 1 trillion years before they existed. This thought is not merely fanciful. It points to something real and important about the relationship between intelligence and the age of the universe. We exist at a particular moment in cosmic time, early enough that the universe is still brightly lit by young and middle-aged stars, early enough that the cosmic microwave background is still detectable and tells us about the Big Bang. Early enough that the large-scale structure of the universe is still visible in the form of galaxy clusters and superclusters rather than having been dispersed by dark energy. We exist at a moment when the universe is still legible, when its history is still written in accessible forms that we can read with our instruments. This legibility is not guaranteed by the laws of physics. It is a feature of our particular moment in cosmic time, and it is a feature that will not last. The beings of the far future, if they exist, will inherit a universe that has hidden most of its history. They will live in Milky or its successor states, surrounded by empty space, with no way of knowing about the spirals that built their home galaxy, no way of detecting the cosmic microwave background that tells us about the Big Bang. No way of measuring the large-scale structure of the universe, because that structure will have been dispersed beyond any causal horizon. They will be cosmologically illiterate, not through any failure of intelligence, but through the simple bad luck of existing too late, after the universe has had time to erase its own records. We, by contrast, exist at a moment of extraordinary cosmological fortune. We can see the cosmic microwave background. We can measure the large-scale structure of the universe. We can detect the gravitational wave background from merging supermassive black holes throughout cosmic history. We can observe galaxies at distances of billions of light years, seeing them as they were billions of years ago, reading the history of the universe in the light of distant objects. We can measure the motion of Andromeda and calculate the future of our galaxy with precision. We exist at the moment in cosmic time when the universe is most readable, most transparent to investigation, most generous with the information needed to understand it, and we have, against extraordinary odds, developed the capacity to do that reading. This capacity, the capacity to understand the universe at the level we are discussing right now, is not something the universe was required to produce. There is no law of physics that mandates the evolution of beings capable of comprehending galactic dynamics, measuring the motion of distant galaxies, and projecting the future of their home galaxy billions of years forward. The universe could have proceeded through its entire history, through the formation of galaxies and stars and planets and the slow burning out of stellar populations and the final coalescence of black holes, without ever producing anything capable of noticing any of it. The fact that it has produced such beings, us, in this moment, is not something that physics predicts or explains. It is simply something that happened, and it happened here, and it happened now, and the window during which it can happen may be narrower than we would like. Because understanding requires not just intelligence, but information, and information requires legibility, and legibility is decreasing with the passage of cosmic time. The window during which a sufficiently intelligent species can, in principle, understand the full history and structure of the universe from observations made within it is not infinite. It is bounded on one end by the time required for stars and planets and biology and intelligence to develop, and on the other end by the time at which the accelerating expansion of the universe begins to hide too much of the cosmos behind causal horizons. We are in that window now. We have been in it for perhaps 100,000 years, since the first members of our species looked up and wondered, and we will remain in it for as long as our civilization continues and continues to direct its attention outward. The Andromeda collision is one of the most dramatic events our galaxy will ever experience, but it is also a reminder of where we stand in the larger story. We are in a galaxy that is old enough to have produced us, but young enough to still be forming stars. We are in a universe old enough to have built the chemical complexity necessary for biology, but young enough to still be legible. We are in a moment of extraordinary cosmic privilege, and we may not always recognize it as such because privilege is most visible in retrospect, most clearly seen when it is gone. Let us now return to the physical details of the merger and trace what happens in the immediate aftermath of the final coalescence of the two galactic cores, because This period, the first billion years or so of Milkymeda's existence as a settled elliptical galaxy, is when the most dramatic physical transformations of the merger are playing out in their final stages. The cores have merged. The black holes have formed a binary and are spiraling together. The starburst is in its late phases, still producing new stars, but at a decreasing rate as the cold gas supply dwindles. The disk structures of both galaxies are completely gone, scrambled by billions of years of gravitational interaction into the disordered, pressure-supported stellar distribution of the elliptical remnant. But the merger is not yet fully complete in a dynamical sense. The stars of both original galaxies, though now mixed together in a single gravitational potential, have not yet fully phase mixed. Phase mixing is the process by which the memory of the initial conditions of a gravitational system is erased through the gradual dispersion of coherent stellar streams into smooth distributions. Stars that were originally part of the Milky Way's disk and that were scattered into elongated, tilted orbits during the merger will still be recognizable as a distinct kinematic population for some time after the merger. Their orbital frequencies will differ from each other and from the orbital frequencies of Andromeda stars, and over time these differences will cause the streams to wrap and shear and dissolve into the smooth background distribution of the elliptical. The timescale for phase mixing depends on the orbital periods of the stars in question. Stars in the inner regions of the merged galaxy on short orbital periods will phase mix quickly, in a few billion years. Stars in the outer regions on long orbital periods will retain their stream-like structure for much longer, potentially for tens of billions of years. The outer halo of Milkymeda will therefore contain the longest-lived fossil records of the merger. Coherent stellar streams whose kinematics still betray their origin in the disrupted disks of the Milky Way and Andromeda long after the inner regions have been thoroughly homogenized. This is not a hypothetical prediction. We can observe exactly this kind of fossil structure in the halos of other elliptical galaxies today. Deep imaging surveys of nearby elliptical galaxies reveal complex networks of stellar streams, shells, and tidal debris in their outer halos, the remnants of past mergers that have been preserved in the outer regions where phase mixing operates slowly. Some of these features are recognizable as the disrupted remnants of spiral galaxies absorbed billions of years ago. Others are more complex, the superposition of multiple merger events, each leaving its own traces. Nay, the outer halo of an elliptical galaxy is an archaeological site, and the tools of galactic archaeology, precision measurements of the positions, velocities, and chemical compositions of individual halos stars, can extract from it a surprisingly detailed record of the galaxy's merger history. Milkymeda's outer halo will be particularly rich in such fossil structures because the merger that created it will have been one of the most massive mergers in the local group's history. The disrupted remnants of the Milky Way's disk and Andromeda's disk will wind themselves around the merged galaxy in great tidal shells and streams, gradually phase mixing over tens of billions of years, but potentially detectable as kinematic substructures for much of that time. If there are beings in Milkymeda billions of years hence with the technology to survey the outer halo in detail, they may be able to reconstruct, from the kinematics of individual halo stars, the fact that their galaxy was formed from the merger of two spirals, and may even be able to determine approximately when the merger occurred and what the orbital geometry of the progenitor galaxies was. They would be reading the autobiography of their galaxy in the motions of its oldest stars. And what that autobiography would tell them is the story we are telling right now, the story of two beautiful spirals that fell toward each other across 2.5 million light years of intergalactic space and merged into the galaxy those future beings call home. They would be the inheritors of the collision, reading its history in starlight, contemplating a past they cannot visit and a future they cannot fully predict, just as we are doing right now in our moment of the same ongoing cosmic story. The question of what those future beings would be like, if they exist at all, is one that connects the astronomical narrative back to the human dimension of this exploration. We have established that most individual stars survive the merger. We have established that the solar system is very likely to persist through the event, its structure intact, even if its cosmic neighborhood is transformed beyond recognition. We have established that the Earth, if it still exists as a habitable world, will be experiencing the merger during a period when the Sun has already evolved significantly from its current state. Let us follow the solar system specifically through the merger timeline and trace what its inhabitants, if any exist, would experience. 4.5 billion years from now, when the first close approach of the two galactic disks begins, the Sun will have been burning its hydrogen fuel for a total of roughly 13.5 billion years, since the Sun is currently approximately 4.6 billion years old. At 13.5 billion years, the Sun will still be on the main sequence, still fusing hydrogen to helium in its core, but it will be noticeably more luminous than it is today. The Sun's luminosity increases slowly over time as the helium produced by fusion accumulates in the core, raising the core temperature and increasing the fusion rate. Over the next 4.5 billion years, the Sun's luminosity will increase by roughly 30 to 40% relative to its current value. This increase in solar luminosity, modest by stellar standards, is catastrophic for Earth's habitability. The amount of sunlight falling on Earth will increase by 30 to 40% over the next 4.5 billion years. The Earth's atmosphere will respond to this increased heating, and the equilibrium temperature of the planet will rise. The exact timeline depends sensitively on the behavior of the carbon dioxide cycle, the geochemical feedback that currently regulates Earth's temperature by adjusting atmospheric carbon dioxide concentrations in response to temperature changes. As the Sun brightens, the increased temperature will cause more rapid weathering of silicate rocks, as drawing down atmospheric carbon dioxide and providing a negative feedback that partially compensates for the increased solar input. But this feedback has limits. Eventually, atmospheric carbon dioxide concentrations will drop to levels too low to support photosynthesis in most plant life. This threshold may be reached in roughly 500 million to 1 billion years from now, well before the Andromeda merger begins. The end of most photosynthetic life on Earth, if it occurs on that timescale, will fundamentally transform the biosphere. The oxygen produced by photosynthesis will gradually be removed from the atmosphere through reactions with the crust and the remaining organic material. The atmosphere will shift from oxygen-rich to carbon dioxide and nitrogen-dominated. Complex. The oxygen-dependent animal life will not survive this transition. Whatever life persists on Earth in the billion-year time frame will likely be microbial, confined to the deep subsurface where liquid water may still exist and where photosynthesis is not required. The surface of the Earth, if still ocean-covered, may still harbour simple marine organisms adapted to the increasingly hostile conditions. By the time the Andromeda merger reaches its most intense phase, roughly 5 to 7 billion years from now, the Sun will have left the main sequence entirely. At roughly 5 billion years from now, the Sun's core hydrogen will be exhausted, and the Sun will begin the transition to a red giant. The core will contract and heat, while the outer layers expand enormously. The Sun's radius will grow to perhaps 100 to 200 times its current value, engulfing the orbits of Mercury and Venus and possibly reaching Earth's current orbital distance. Whether Earth itself is swallowed depends on the details of the red giant expansion and on how much mass the Sun loses through stellar winds during the red giant phase, which is uncertain. If the Sun loses mass during the red giant phase, which it will, the gravitational force it exerts on Earth will decrease, and Earth's orbit will expand outward as a result. This orbital expansion may carry Earth just far enough from the expanding Sun to avoid direct engulfment, even if the Sun's outer layers reach Earth's current orbital distance. But even if Earth escapes engulfment, its surface will be baked by the intense radiation of the nearby red giant Sun, raising temperatures to levels thousands of degrees above any possibility of liquid water. Whatever life or remnant biology existed on Earth's surface will not survive the red giant phase. The red giant phase of the Sun will last roughly 1 billion to 2 billion years, during which the Sun will lose the majority of its remaining mass through powerful stellar winds, ejecting this material into the surrounding space as a planetary nebula. What remains at the center after the nebula dispersal will be the Sun's hot, degenerate core, a white dwarf with a mass of roughly half to 60% of the Sun's current mass and a radius comparable to Earth's, glowing blue-white with stored thermal energy and cooling slowly over billions of years. Earth, if it still exists as a rocky body, will orbit this white dwarf at a distance of perhaps 1 to 2 astronomical units, a cold, airless, sun-blasted relic of what was once a living world. The merger of the Milky Way and Andromeda will therefore be experienced by the solar system in a state very different from its current configuration. The Sun will be a white dwarf, Earth will be a cold rock in orbit around it, or possibly will have been disrupted by the solar mass loss and sent into a different orbit, or possibly will have been perturbed by the gravitational interactions of the merger itself. Other planets in the solar system will similarly have had their orbits modified by the mass loss of the Sun and potentially by gravitational perturbations from stellar encounters during the merger. And the probability of the solar system experiencing a close stellar encounter during the merger is low, but not negligible. We established earlier that the probability of a direct collision between any two stars during the merger is extraordinarily small. But a close encounter, meaning a passage of another star close enough to significantly perturb the planets in the solar system, is more probable than an actual collision. How much more probable depends on what counts as significant perturbation and what distance of closest approach constitutes a threatening encounter. For the outer solar system, particularly for planets and objects in the Kuiper belt and Oort cloud at distances of tens to hundreds of astronomical units from the Sun, a stellar encounter at a distance of a few thousand astronomical units, which is still a tiny fraction of a light year, could significantly perturb their orbits. Such encounters are rare under current conditions, but would be somewhat more frequent during the merger, when the local stellar density in certain regions of the combined galaxy may be temporarily elevated. The inner planets, including the remnant of Earth if it still orbits the white dwarf sun, are gravitationally much more tightly bound and would require a far closer encounter to be significantly affected. The long-term fate of the solar system within Milky is therefore a story of gradual isolation rather than dramatic destruction. The white dwarf sun will cool over billions of years, fading from blue-white to yellow to orange to red, its luminosity diminishing by orders of magnitude as its stored thermal energy is radiated away. The planets that remain in orbit around it will cool proportionally, their surfaces dropping to temperatures approaching absolute zero as the energy input from the central object dwindles toward negligibility. The solar system will become a dark, cold collection of rocky and icy bodies orbiting a dim, fading ember, drifting through the outer regions of Milky on whatever orbit the gravitational perturbations of the merger have left it with. The timescale over which a white dwarf cools to temperatures too low to emit significant visible light is roughly 10 to 15 billion years for a white dwarf of solar mass. This means that the solar white dwarf, formed perhaps 6 to 7 billion years from now during the Sun's red giant phase, will still be emitting faint, visible light during the most intense phases of the Andromeda merger. It will be a dim, cool object by then, a white or pale yellow point of light, rather than the blazing yellow-white star we see today, but it will not yet be a black dwarf. The cooling curve of a white dwarf is asymptotic, approaching absolute zero ever more slowly, meaning that no white dwarf in the current universe has yet had time to cool all the way to a true black dwarf state. The universe is simply not old enough, and the first true black dwarfs will not exist for at least a few quadrillion years, far longer than the current age of the universe. The solar system's long-term fate within Milky is therefore one of the following possibilities, each with a different probability, and astronomers cannot currently determine which will actually occur because the details depend on the specific trajectory the solar system takes through the merger and on the cumulative effect of gravitational perturbations over billions of years. In the most likely outcome, the solar system drifts through the outer regions of Milky largely undisturbed, except for gradual orbital evolution driven by distant gravitational interactions. The white dwarf sun cools and dims. The planets cool. The system persists as a cold, dark collection of bodies for trillions of years. Eventually, over timescales of 10 to the power of 19 years or longer, gravitational interactions with other stars in the galaxy will slowly modify the solar system's orbit through the galaxy itself, potentially ejecting the solar system from Milky entirely into intergalactic space, where it will drift alone in the void for the remainder of the universe's usable lifetime. In a less likely but possible outcome, the solar system experiences a close gravitational encounter with another stellar system during the merger, which perturbs the orbits of the planets significantly. Some planets may be ejected from the solar system into interstellar space, becoming rogue planets drifting through the galaxy without a stellar host. The remaining planets may be left in highly elliptical, less stable orbits around the white dwarf. In the most extreme version of this scenario, the solar system is completely disrupted, its planets scattered in all directions by the encounter, the white dwarf left alone to cool in isolation, while the former planets drift through the galaxy as cold, dark, isolated rocky bodies. In yet another possible outcome over the very long time scale of 10 to the power of 15 years, the orbital energy of the solar system within Milky will be slowly sapped by gravitational wave emission from the orbital motion of the white dwarf sun around the galactic center, combined with the dynamical friction of the surrounding stellar population. This will cause the solar system's orbit to decay very slowly, spiraling inward toward the center of Milky over timescales so vast that they are difficult to even express meaningfully. Eventually, if the system persists long enough, it may spiral all the way to the center and be disrupted by the tidal forces of the central supermassive black hole, or even be swallowed by it. But this outcome requires timescales of 10 to the power of 20 years or more, so incomprehensibly far in the future that the universe will have changed in ways we cannot fully predict by then. The point of tracing these possibilities is not to predict which one will actually occur, since we cannot know with confidence, but to illustrate the character of the solar system's long-term fate. It is a fate of gradual cooling, gradual isolation, gradual fading into the cold, dark future of a universe that is running down. The merger does not end the solar system. It does not directly destroy the Earth or scatter the planets. What it does is place the solar system in a new galactic context, one that is less fertile, less active, less generative than the one we currently inhabit, and leave it there to age at its own pace. Now, let us zoom back out to the galaxy scale and consider what Milky looks like, not just in the immediate aftermath of the merger, but across the full span of its future existence. We have established that Milky will be a massive elliptical galaxy, red and slowly dimming, with a stellar population that is aging and dying without significant replacement. We have established that it will be increasingly isolated in an expanding universe, surrounded by growing expanses of empty space, as dark energy pushes distant galaxies beyond the cosmological horizon. We have established that its central black hole, now a single merged object of somewhere between 150 and 200 million solar masses, will be quiescent after its post-merger active phase, accreting only the occasional star or cloud of hot gas that wanders too close to the galactic center. What we have not yet fully described is the very long-term evolution of the stellar population itself, and what Milky ultimately becomes as its stars age and die over timescales that dwarf the current age of the universe. This is the territory of what cosmologists sometimes call the degenerate era, and the black hole era, the far future epochs of the universe described in careful detail by the cosmologists Fred Adams and Gregory Laughlin in their rigorous treatment of the long-term future of the universe. The picture they paint, drawing on the physics of stellar evolution, gravitational dynamics and thermodynamics, is worth tracing here because it is the ultimate destination of everything we have described. The final chapter of the story that begins with two beautiful spirals falling toward each other across intergalactic space. In the current stelliferous era, the universe is characterized by the activity of stars. Stars burn nuclear fuel, produce light, maintain planetary temperatures, and provide the energy gradients that complex systems, including living systems, can exploit. The stelliferous era began with the formation of the first stars roughly a few hundred million years after the Big Bang, and will end when the last stars exhaust their fuel. The end of the stelliferous era for the universe as a whole is roughly 10 to the power of 14 years from now, which is 100 trillion years. At that point, the last red dwarf stars, the most miserly consumers of hydrogen fuel, will have exhausted their supply and will begin the transition to white dwarf remnants. The universe will go dark in the sense that no new stellar light will be produced. The remaining sources of light will be the cooling, white dwarfs, which will persist as progressively dimmer and cooler objects for an enormous additional span of time before finally fading to black dwarfs that emit no detectable radiation. Milkomeda will experience the end of its stelliferous era somewhat before the universe as a whole does, because the merger will have consumed its cold gas supply earlier than a non-merging galaxy would have. The starburst accelerates the consumption of the raw material for star formation, though advancing the clock on the eventual cessation of star-forming activity. By the time the last red dwarf in Milkomeda finally exhausts its hydrogen fuel, the merged galaxy will have been in a state of declining star formation for tens of billions of years, having used up its gas in the merger starburst and subsequent low-level star formation activity. But the red dwarfs, even as they begin to die, do not do so quickly. The transition from the main sequence to the white dwarf stage for a red dwarf of very low mass is itself slow by comparison to the transitions of more massive stars. A red dwarf does not swell into a red giant in the way that the Sun will. It simply exhausts its hydrogen fuel, brightens slightly as the core contracts and heats, and then gradually contracts into a helium-white dwarf without passing through a giant phase. And the transition is undramatic and slow, and the resulting white dwarf is smaller and less massive than the white dwarfs produced by sun-like stars. After the last stars have died, Milkomeda will enter its degenerate era, populated by cooling white dwarfs, neutron stars, and stellar mass black holes, all embedded in the gravitational potential of the central supermassive black hole and the vast dark matter halo. The white dwarfs will cool over timescales of 10 to 14 billion years toward temperatures approaching absolute zero, eventually becoming black dwarfs. The neutron stars will cool similarly, their surfaces dropping from the millions of degrees they had immediately after formation to temperatures far below what any current instrument could detect. The stellar mass black holes will simply drift through the galaxy, accreting occasionally from the diffuse gas of the halo and growing imperceptibly larger with each accreted particle. In this degenerate era, the galaxy will be extraordinarily dark and cold by any measure familiar to us, but it will not be completely static. Gravitational interactions between the stellar remnants will continue, driven by the random motions of billions of objects through the combined gravitational potential of the galaxy and its dark matter halo. Occasionally, a white dwarf or neutron star will be scattered by a close encounter with another remnant into a more tightly bound orbit that brings it closer to the center of the galaxy, where it may eventually be swallowed by the central black hole. Occasionally, an object will be scattered into a less bound orbit and eventually ejected from the galaxy entirely. Over the timescales of the degenerate era, measured in tens to hundreds of trillions of years, the galaxy will gradually lose mass through this slow evaporation process, its outermost objects being ejected one by one into intergalactic space. The central supermassive black hole will grow slowly during the degenerate era, accreting whatever material is scattered close enough to the galactic center. Its mass will increase from its post-merger value of roughly 200 million solar masses to something larger, though not dramatically larger, since the rate of accretion in a galaxy devoid of cold gas and with a depleted stellar population is very low. The black hole will be the last major structure remaining in Milkomeda as the degenerate era progresses, because all of the stellar remnants that are not ejected into intergalactic space will eventually find their way to the center through dynamical friction and be swallowed, adding their mass to the growing black hole. Eventually, Milky will consist almost entirely of its supermassive black hole and its dark matter halo, with most of the stellar remnants either ejected or swallowed. The dark matter halo itself will be slowly eroded by the same dynamical processes, its outermost particles scattered to larger and larger radii until they escape the system, while inner particles spiral toward the center and are eventually swallowed by the black hole. But dark matter, interacting only gravitationally, is subject to these processes on very long timescales, and the dark matter halo of Milky will persist for an extraordinarily long time, far longer than the stellar population, and then there is Hawking radiation. In 1974, the British physicist Stephen Hawking derived one of the most profound results in theoretical physics, a result that connects quantum mechanics, thermodynamics, and general relativity in a way that is still not fully understood. Black holes are not perfectly black, Hawking showed. Quantum mechanical effects near the event horizon of a black hole cause the black hole to emit thermal radiation, a faint glow of photons and other particles at a temperature inversely proportional to the black hole's mass. The more massive the black hole, the lower its Hawking temperature, and the slower it emits radiation. For a stellar mass black hole of a few solar masses, the Hawking temperature is roughly 60 nanokelvin, far below the current temperature of the cosmic microwave background, meaning the black hole is currently absorbing more radiation from the universe than it emits, and is therefore growing rather than shrinking. But as the universe continues to expand and cool, the temperature of the cosmic microwave background will drop below the Hawking temperatures of stellar mass black holes, and those black holes will begin to lose mass to Hawking radiation. The evaporation of stellar mass black holes takes roughly 10 to the power of 67 years, which is so far in the future that every other process we have discussed will have long since concluded before it begins. For a supermassive black hole of the mass of Milky's central black hole, but then the Hawking temperature is so low and the evaporation timescale so long that the numbers approach incomprehensibility. A black hole of 200 million solar masses has a Hawking temperature of roughly 10 to the power of negative 17 Kelvin. A temperature so close to absolute zero that expressing it meaningfully is almost impossible. Its evaporation timescale, the time for it to completely evaporate through Hawking radiation, is roughly 10 to the power of 97 years. This number is so far beyond any timescale we have discussed that all the previous timescales, the 4.5 billion years to the first close approach, the 13 billion years of the current age of the universe, the 100 trillion years of the stelliferous era, the trillions of years of the degenerate era. All of these are so small relative to 10 to the power of 97 years that they are essentially zero in comparison. But Milky's black hole will eventually evaporate. The laws of physics, as currently understood, do not allow a black hole to persist forever. Hawking radiation is real even if it has never been directly observed for macroscopic black holes, and given enough time, even the most massive black hole in the universe will evaporate. The final moments of a black hole's evaporation, as its mass decreases to very low values and its temperature and luminosity skyrocket, will be a brief and intense flash of radiation, the universe's last fireworks from a source whose progenitor galaxy formed billions of years before from the merger of two spiral galaxies that fell toward each other across intergalactic space. After that flash, there will be nothing left of Milky. Not the stars, not the black hole, not the dark matter halo, which will have long since dispersed. Everything that was once the Milky Way and Andromeda, everything that was once a trillion stars and billions of years of stellar evolution and the chemical complexity that gave rise to life and minds, everything will have been converted to radiation and scattered into the vast, cold, empty universe. The matter will still exist in some sense as photons and fundamental particles, but the organization will be gone. The arrangement will be gone. The galaxy that was built by gravity over billions of years will have been undone by entropy and quantum mechanics over time scales that make the age of the universe seem like an eye blink. This is the ultimate destination. This is where the story ends, not with a bang, not with a whisper, but with a final faint flash of hawking radiation from the last black hole in what was once a galaxy, in a universe that has grown cold and dark and empty, that has forgotten everything it once contained, that has no remaining structure capable of noticing that it once held within it something extraordinary. But we are not at that destination. We are at the beginning. We are 4.5 billion years before the first close approach of two galaxies that are right now living out their separate lives, forming stars and cycling gas and hosting whatever forms of complexity their planetary systems may support. We are at a moment when both galaxies are intact, when the spiral arms of the Milky Way are real and present and turning slowly overhead on every clear night, when Andromeda is a faint smear of light that requires knowing where to look, not yet close enough to show its disk to the naked eye, not yet dominating the sky, still distant enough to seem harmless. The distance of Andromeda is one of the most philosophically interesting numbers in astronomy. 2.5 million light-years. It means that the light we see when we look at Andromeda tonight left that galaxy 2.5 million years ago. It means we are seeing Andromeda as it was 2.5 million years in the past, when our ancestors were small-brained bipeds who had not yet mastered fire, who had no language, no art, no astronomy, no concept of the universe beyond the immediate savanna and forest. The galaxy we see is a ghost. It is the image of something as it was, not as it is. And the question planted at the opening of this exploration, the question of what Andromeda looks like right now, in this very moment, can now receive a partial answer. Right now, at this very moment, Andromeda is 2.5 million light-years closer to us than when the light we are seeing tonight left it. It has been moving toward us for 2.5 million years since that light departed at 110 kilometers per second. In 2.5 million years, at 110 kilometers per second, Andromeda has closed the distance by approximately 8.7 trillion kilometers, which is less than 1 light-year, a negligible fraction of the total distance. Andromeda right now looks essentially the same as it does in our 2.5 million-year-old image of it. The approach has made no perceptible difference to its appearance or structure over this interval. But here is the deeper answer to the question, what is happening in Andromeda right now at this moment that we cannot see? The answer is everything. Every star in Andromeda is at some point in its life that we cannot know. Stars that were alive when the light we see tonight departed Andromeda may have died since then. New stars may have formed. The supernovae, the novas, the stellar mergers, the planetary systems forming around young stars, the potential chemistries and biologies on the surfaces of those planets, all of that is happening right now in Andromeda, at this moment, and we cannot know any of it. We are separated not just by distance, but by the fundamental speed limit of the universe. The information about what Andromeda is like right now is travelling toward us at the speed of light, and it will arrive in 2.5 million years. This delay, this cosmological epistemic barrier imposed by the finite speed of light, is not just a practical inconvenience. It is a fundamental feature of the universe we inhabit, a feature that has profound implications for what it means to know something about the cosmos. We can never observe the universe as it is simultaneously. We can only observe it as it was, at various depths of look-back time determined by the distances to the objects we observe. The nearby moon we see as it was slightly more than 1 second ago. The sun as it was 8 minutes ago. The nearest stars as they were years ago. Andromeda as it was 2.5 million years ago. For the most distant galaxies detectable by our best telescopes as they were more than 13 billion years ago, when the universe was less than 1 billion years old. The universe we observe is not a snapshot of the present, it is a palimpsest of the past, a layered record of different moments in cosmic history overlaid on top of each other and assembled by the finite travel time of light into what appears to be a single, coherent picture. The coherence is an illusion of scale. On the scales of everyday life, the speed of light is so fast that the delay between emission and observation is imperceptible. On cosmic scales, the delay becomes the dominant feature of observation. The universe reveals itself to us, not as it is, but as it was, and the distinction between those two things grows larger with every light year of distance. This is the context in which we understand the Andromeda collision. We see Andromeda as it was. We calculate its trajectory based on measurements of its past light. We project the future of the merger based on the physics we have derived from observations of the past. We are reasoning about the future from the past, using the present as a vantage point from which we can barely see either end of the story. The collision itself will begin in a future we will never directly experience and be resolved in a future so remote that no descendant of any currently living being will witness it either. We are observers of a process so slow that our entire species' history, from the first stone tools to the present moment, is less than 1/10,000,000th of the time remaining before the first close approach. And yet we know about it. We have measured it, modelled it, and understood it in detail sufficient to write these words. This capacity for temporal reach, the ability to reason about events billions of years in the future and billions of years in the past, is one of the most extraordinary things about the kind of intelligence that has emerged on this planet. We are not bound by our direct experience in the way that every other known form of life is. We can extend our cognition backward to the Big Bang and forward to the evaporation of black holes, traversing in thought timescales that dwarf the operational range of any biological system. This temporal reach is purchased at the price of directness. We do not experience deep time. We reason about it, we construct it from mathematics and observation and physical law, and we hold it in our minds as a kind of extended present that encompasses the entire history and future of the universe in a single, simultaneous understanding. The Andromeda collision is one of the most powerful demonstrations of this capacity. It is an event that has not happened, that will not happen for 4.5 billion years, that will last for 2 billion years after it begins, and that we understand in considerable detail, despite never having experienced it and never being able to experience it directly. We understand it because the physics that governs it is the same physics that governs the motion of a ball thrown across a room, the same physics that explains the orbit of the moon, the same physics that describes the behavior of matter and energy at every scale in this universe. The universality of physical law is the bridge that allows finite, short-lived beings to comprehend events of cosmic scale and duration. And now we come to the place where everything we have discussed converges. The factual and the philosophical, the astronomical and the existential, the precise measurements and the unanswerable questions. We come to the deepest layer of what the Andromeda collision means, not just as an astronomical event, but as a fact about the universe and our place in it. The title of this exploration promises that nothing survives. We have spent an enormous amount of time building toward a full understanding of what that means, and now we can state it with complete precision. The stars survive, the matter survives, the atoms survive, the dark matter halos survive and merge into one. The supermassive black holes survive and merge into one. The solar system very likely survives. The atoms in your body will be somewhere in Milky Way billions of years from now, distributed perhaps among different stellar systems or floating in the hot gas of the galactic halo, but conserved, as matter is always conserved in the physical universe. What does not survive is the arrangement. What does not survive is the organization. What does not survive is the specific, historically contingent configuration of matter and motion that constitutes the Milky Way as a living, generative, star-forming spiral galaxy, with its specific history, its specific chemical evolution, its specific population of stars and planets, its specific place in the local group, its specific relationship to Andromeda across 2.5 million light-years of intergalactic space. That configuration is ending. That arrangement is being dissolved. That organization is being transformed into something else, something that contains all the same matter, but none of the same structure, none of the same dynamical character, none of the same generative capacity. And here is the thought that has been waiting at the bottom of everything we have discussed. Every complex thing in the universe is an arrangement. You are an arrangement. A living human being is a specific configuration of atoms organized by chemistry and biology and evolution into a structure of extraordinary complexity and improbability. A civilization is an arrangement. A culture is an arrangement. Every relationship, every work of art, every idea, every moment of understanding is a specific configuration of matter and energy and information that exists briefly and then dissolves. The universe does not preserve arrangements. It conserves matter and energy because the laws of physics require it to. But the specific organizations that matter and energy fall into, the arrangements, the patterns, the structures, those are temporary. They arise under particular conditions and dissolve when those conditions change, and the conditions always change. The Andromeda collision illustrates this truth at the grandest available scale. Two galaxies, each a specific arrangement of hundreds of billions to trillions of stars, each the product of billions of years of gravitational and chemical evolution, each hosting in its current form whatever complexity and life its planetary systems support, will be dissolved into a new arrangement that carries their matter but not their character. The dissolution is not destruction, it is transformation. But transformation at this scale, on these time scales, is as complete and as irreversible as any destruction. The Milky Way will not become something else and then return to what it was. It will become something else and remain something else for the rest of the universe's functional lifetime. The transformation is terminal. What makes this contemplation bearable, what keeps it from collapsing into despair, is the recognition that the impermanence of arrangements is not a defect of the universe. It is the precondition for everything interesting about it. A universe of permanent, unchanging arrangements would be a universe of nothing. Change is what generates complexity. The cycling of matter through stars and supernova and molecular clouds and new stars is what builds chemical complexity from simple beginnings. The merging of galaxies is what drives the growth of supermassive black holes and the creation of environments in which complexity can flourish. The impermanence of individual arrangements is the engine of the universe's increasing complexity on the largest scales, even as on smaller scales it means the dissolution of every particular beautiful thing. The Milky Way is a beautiful thing. It is our home in the deepest sense, the structure that provided the conditions for our star to form, for our planet to exist, for the chemistry of life to emerge, for billions of years of evolution to produce the kind of intelligence that can look up at the night sky and understand what it is seeing. It will not last forever. Nothing lasts forever in this universe, but it has lasted long enough for us to exist within it, and it has provided us with enough time and enough stability and enough chemical richness to become the kind of beings who can comprehend their own galaxy and its fate. That is not nothing. That is, in the full scope of what the universe might have produced, something extraordinary. The beach at night, the Milky Way overhead, from horizon to horizon, too bright and too detailed to be accounted for by any simple description. And now, knowing what you know, you can see it differently. You can see it not just as a beautiful band of light, but as a specific arrangement of 300 billion stars organized by gravity into a flat, rotating disk with spiral arms and a central bulge and a dark matter halo extending hundreds of thousands of light years in every direction. You can see it as a living system forming new stars and cycling material and hosting on its planets whatever forms of chemistry and complexity the long history of stellar evolution has made possible. You can see it as something temporary, a configuration of matter that has been building for 13 billion years and will begin dissolving in 4.5 billion more. You can see it as something that knows itself, at least in this one location, at least in this one moment, and in the constellation Andromeda, you can find the faint smear of light that is the other great galaxy of the local group, 2.5 million light years away. Its light, 2.5 million years old by the time it reaches your eye. The galaxy as it was rather than as it is, falling toward you at 110 kilometers per second in a trajectory that was established by the geometry of the early universe, and that nothing in the local cosmos has the power to alter. You cannot feel it moving. You cannot detect its approach in any way that does not require extraordinarily precise instruments. But it is there, and it is coming, and what it will do when it arrives is something you now understand in a way that very few beings in the history of life on Earth have understood. The collision will not burn the stars. It will not destroy the solar system. It will not annihilate the matter of either galaxy. What it will do is end the arrangement, end the organization, end the specific, historically contingent, improbably beautiful configurations of matter that are the Milky Way and Andromeda. It will produce from their dissolution something new and something quieter and something that will age slowly in an increasingly empty universe, its stars fading one by one over trillions of years, its final black hole evaporating and a last flash of Hawking radiation so far in the future that the number of years involved has more digits than there are atoms in the observable universe. And the atoms that are in your body right now will be part of that story, not you. The arrangement that is you is far more fragile than the arrangement that is the Milky Way, and it will dissolve long before the galaxies meet. But the atoms, the carbon in your cells, forged in the interior of a star that lived and died before the sun formed. The oxygen you are breathing, produced by the photosynthesis of organisms that lived hundreds of millions of years ago. The iron in your blood, scattered into the interstellar medium by a supernova explosion billions of years before the solar system existed. Those atoms will persist. They will cycle through the merger. They will be incorporated into new stars born in the starburst, or dispersed into the hot halo of Milkomeda, or locked inside the remnant of the cooling white dwarf that will be all that remains of the sun. And eventually, after trillions of years of cooling and fading and the slow evaporation of the last black hole, those atoms will be released as radiation into a cold, dark, empty universe that has no remaining structure capable of being surprised by anything. But right now, those atoms are arranged into something that can be surprised, something that can look up at the night sky and feel the scale of what it is seeing, something that can receive the ancient light of a distant galaxy and know with precision and certainty and genuine understanding what that galaxy is, where it is going, what it will do when it gets here, and what that means for the improbable arrangement of matter that is doing the looking. That is what nothing surviving means. Not the end of the atoms, the end of the arrangement, the end of the specific, unrepeatable, historically irreplaceable configuration of matter and motion that is the Milky Way and the Andromeda galaxy that is falling toward it, and the solar system that orbits quietly in one of its spiral arms, and the planet that circles that solar system's star, and the beings on that planet who have spent the long history of their brief existence looking up and wondering what is out there, and finding, to their astonishment and their gratitude and their quiet, irreducible awe, that the answer is everything, and that everything is coming. We are the part of the Milky Way that knows what is happening to it, for now, and for this extraordinary, fleeting, cosmically improbable moment. That is enough. That is more than enough. That is, in the full and honest accounting of what the universe might have produced and what it actually has produced, very close to a miracle. Not a miracle that suspends the laws of physics. A miracle that operates through them, that emerges from hydrogen and time and gravity and nuclear fire. That requires billions of years of stellar processing and billions more of biological evolution, and that results, here and now, in something looking back at the universe with understanding and with wonder. The Andromeda galaxy is falling toward us. It has been falling toward us since before the sun existed. It will arrive in 4.5 billion years, and when it does, nothing will survive. The arrangements will end. The patterns will dissolve. The organizations will be transformed into something new and something quieter, and something that will age in the dark for longer than we have words to describe. But we know about it, and knowing is itself a form of the universe being here, a form of the cosmos being present to itself, a form of the arrangement, however temporary, mattering. The light of Andromeda crosses 2.5 million light-years of empty space and arrives at the eye of something that understands what it is. For one moment, in the history of the universe that happens, and the laws of physics do not require it to, and the laws of physics do not forbid it, and here we are.